Va, pero sigue escuchándose.
Eso es.
No creo que. ¿Y qué ponemos aquí? ¿Ale? ¿Qué ponemos aquí? ¿Pero tú lo vas a poner?
Ajá, ya lo voy a poner.
Ah,
Va a
ok.
compartir pantalla.
Va.
Bueno, no está saliendo. Sí, hay que
Déjame.
regresarlo, ¿no? ¿No lo silenciaste?
Sí, el micrófono.
Ah.
Hola. Eso sí se escucha.
Hola, soy Tatiana Fiordelicio, soy bióloga de la facultad y soy responsable del Laboratorio Nacional de Soluciones Biomiméticas para Diagnóstico y Terapia. La ciencia se construye a partir del conocimiento colectivo y eso es lo que hacemos en este laboratorio. En este laboratorio juntamos físicos, matemáticos, biólogos, químicos, médicos y muchos otros de otras disciplinas para poder realmente desarrollar soluciones a los problemas que hoy en día tenemos y que son muy complejos y requieren del esfuerzo de todo el mundo. Somos un laboratorio formado por personas apasionadas y preocupadas por su entorno. Queremos construir un mundo mejor y que tú lo construyas con nosotros. Vuélvete parte.
presentar a nuestro siguiente ponente.
Hola, ay, ¿ya puedo esto? Hola, gracias a todos por venir y bueno, ahorita Diego nos va a dar una plática acerca de lo que hacemos en el laboratorio. Diego Zamarrón es el responsable de la unidad de biología molecular del laboratorio, es físico y pues seguramente nos va a decir cosas muy interesantes.
Perfecto. Muchas gracias, Jim. Bueno, yo soy Diego Zamarrón. Les voy a hablar un poquito del laboratorio. El laboratorio se llama Laboratorio Nacional de Soluciones Biomiméticas para Diagnóstico y Terapia, LANSBIODIT para corto. Ay, ¿qué pasó? Se me fueron las... Ok, un momento. Mejor uso el inalámbrico para que no se mueva esto. Ok.
Estás hablando del HDMI.
Ya. Ok. Voy a usar el inalámbrico. ¿Me lo pasas, Jimé, por favor? Muchas gracias. Bueno, ahora sí. Ok. Muy bien. Voy a empezar un poco con la historia del Laboratorio Nacional. El Laboratorio Nacional, como todos los otros laboratorios nacionales, se creó a partir de una iniciativa de parte de CONACYT para mejorar, digamos, las capacidades nacionales y generar muchos laboratorios con infraestructura y recursos humanos para estar, digamos, en la punta de ciertas partes de la investigación. Entonces, en el caso específico del Laboratorio Nacional, nos aliamos con el INER y con el Instituto de Nutrición para hacer sobre todo investigación en biosensores, en preservación de órganos y en modelos de cultivo muy específicos que se ha trabajado en muchos órganos diferentes. Eh, la idea original del laboratorio es poder hacer desarrollo, es decir, no quedarse en la parte de investigación, sino llevar ese desarrollo a algo tangible. Es por eso que, digamos, el ecosistema en el que está inmerso implica muchas otras cosas, tales como pueden ser agencias regulatorias como la COFEPRIS o la FDA, desde luego todos los institutos de salud, que son los que tienen las necesidades que nosotros buscamos solventar, y bueno, desde luego también fondos de dinero, tanto nacionales como extranjeros, para poder llevar a cabo esto. Ahora, ¿quiénes somos los que estamos desarrollando todo esto? O bueno, ¿qué es el LANSBIODIT? Entonces, ahí están la misión y la visión del LANSBIODIT, que la idea es desarrollar soluciones de inspiración biológica que transformen todo lo que desarrollamos en la investigación en productos que puedan tener un impacto social, que puedan ser algo en lo que se pueda utilizar directamente, ¿no? Y para eso vamos a recurrir mucho a la colaboración con otros grupos de trabajo. Entonces, eso es lo que nosotros buscamos hacer, ¿no? Tener la capacidad de estar liderando, digamos, el desarrollo de tecnologías para la salud. Entonces, ¿cómo hacemos esto? Lo que buscamos es desarrollar ideas en el laboratorio que a las cuales podamos nosotros agregarle valor con el know-how que hemos desarrollado al implementar diferentes técnicas de fabricación, diseño, demás, pasar a través de programas que nos ayuden a desarrollar esa tecnología al punto de poder ser, para empezar, protegidas y luego trasladadas al mercado, ¿no? Entonces, ese es el objetivo del Laboratorio Nacional. La organización del laboratorio está dentro de la facultad, pero depende también de la coordinación de la investigación científica, por ser un laboratorio nacional, y también claramente de CONACYT, porque es de ahí de donde sale el programa de laboratorios nacionales. El laboratorio está dividido en dos partes grandes. Una parte que es la parte de investigación, que no es de manera directa hecha, digamos, por los miembros básicos del LANSBIODIT, sino se da a través de colaboraciones con otros investigadores. Entonces ahí hay 3 de ellos, ¿no? Colaboraciones con el INER, con el laboratorio ah, de fibrosis y con el laboratorio de endocrinología comparada. Entonces, esos son algunos de de las colaboraciones con las que trabajamos para desarrollar la parte de investigación, y la otra parte es la parte de desarrollo. Entonces, la parte de desarrollo se da como servicio y está dividida en 3 partes, que es la unidad de biología molecular y diagnóstico, la de micro y nanotecnología, perdón, fabricación, y la de imagenología cuantitativa. Ahorita vamos a hablar un poquito más de ellas. No sé qué pasó. Ah, es que no puedo porque... Eso, gracias. Perdón. Es que me estás moviendo la presentación, Ale.
Que necesito
Sí.
mover ahí.
Ya. Entonces, bueno, son las 3 unidades, la UNIFAB, la UNICUA y la UNIBIM. En cada una se desarrollan actividades diferentes. Y si me da chance, Ale, le podemos cambiar de diapositiva. Perfecto. A grandes rasgos, esto es lo que se hace en cada una de ellas. En la unidad de fabricación se hace desde la caracterización de materiales, la fabricación de estructuras en diferentes escalas, desde nano hasta meso, la caracterización física de materiales y de lo que se fabrica, e incluso caracterización biológica, como pruebas de biocompatibilidad, de citotoxicidad, demás. Entonces, en la UNICUA es la que administra toda la parte de microscopía del Laboratorio Nacional, entonces tienen todas las capacidades de microscopía del laboratorio, se cuenta con muchos equipos de microscopía de epifluorescencia, se tiene un microscopio que puede mantener condiciones de cultivo y hacer un registro de un cultivo celular a lo largo de varios días. Se tiene también un microscopio confocal que ha producido imágenes muy buenas, y de esas imágenes se han salido 2 portadas de revista, lo cual estamos muy orgullosos de. Y la unidad de biología molecular y diagnóstico, en donde se tienen todas las, digamos, los métodos de detección de proteínas y ácidos nucleicos básicos. Se da también un servicio de diagnóstico. En este momento solo está SARS-CoV-2, pero próximamente vamos a incluir también la detección del virus de papiloma humano. Y se hacen, una de las cosas importantes de la unidad de biología molecular es que se pueden masificar pruebas. Entonces podemos hacer pruebas de manera masiva de cualquiera de estas técnicas. Entonces, bueno, tenemos un equipo de trabajo que es multidisciplinario. Tenemos gente de física, de biología principalmente, pero también de matemáticas, de química y de ingeniería. Entonces, tenemos un equipo muy completo que nos ayuda a atacar problemas complejos desde muchos lados distintos. Además, tenemos una buena relación de cantidad de gente entre hombres y mujeres, lo cual es también muy bueno. Entonces, algunas de las otras colaboraciones que hacemos con otros investigadores tienen que ver con el desarrollo de diferentes plataformas para cultivo en diferentes tipos de órgano, ¿no? Entonces tenemos trabajos para pulmón, tenemos trabajos de fibrosis, de hígado, de sistema nervioso, de morfogénesis, de páncreas, de sistema neuroendocrino, y entonces trabajamos con muchos diferentes investigadores para poder llevar a cabo este tipo de desarrollos. Esos trabajos pueden ser tanto nacionales como internacionales. Hemos trabajado dentro de la universidad con muchos investigadores, dentro del país también con algunos investigadores y con algunas empresas para desarrollar soluciones a su medida, pero también internacionalmente, como con la Universidad de Cali o el proyecto internacional con la comitiva francesa que se encuentra acá, que es la razón de una buena parte de la razón de este simposio. Entonces, todo esto lo hacemos a través de brindar servicios y estos servicios los damos utilizando este principio. Nosotros recibimos ideas, necesidades, especificaciones de lo que se busca y a partir de eso nosotros ayudamos a diseñar una solución. Esa solución se simula para asegurar que el diseño está bien hecho. Después eso se fabrica o se instrumenta, porque podemos fabricar estructuras o desarrollar pequeños equipos. Y después eso se caracteriza, tanto física como biológicamente, ¿no? Que haga lo que tiene que hacer, como dice que se tiene que hacer, y que tenga el efecto que se busca que tenga en los tejidos específicos para los que se diseñó, ¿no? Además, todo esto se hace bajo procesos certificados bajo la norma ISO 9001, entonces eso es para asegurar la calidad del resultado que se está entregando. Algunas de los proyectos grandes que tenemos andando en el laboratorio son principalmente, que es el proyecto de colaboración con Francia, específicamente con el AI y el Laboratorio de Inflamación y Adhesión que está en Lumini, y con la Universidad Sorbona, a través de Matthew, que antes era el responsable del Laboratorio Nacional. Entonces, aquí estamos trabajando en desarrollar plataformas que nos permitan evaluar justamente cómo estímulos mecánicos tienen efecto en el sistema inmune. Entonces, vamos a hablar de eso, van a hablar un poco más tarde algunos de los integrantes del laboratorio. Entonces, rápidamente, algunas de las cosas que se hacen en la unidad de fabricación son caracterización, como había mencionado, que pueden ir desde microscopía de fuerza atómica o microscopía de barrido, que con esas es con las que se obtiene imágenes como esta, que no se alcanza a ver, pero es una reproducción de un virus en una escala de alrededor de 20 micras, entonces se tiene mucho detalle en cosas muy chiquititas y se pueden ver con este SEM que tenemos. Es un SEM chiquito, pero se puede ver. Tenemos perfilometría, lo cual nos permite validar muchos de los métodos de fabricación que tenemos. Un método muy interesante que es la tomografía de coherencia óptica, que nos permite obtener, literalmente hacer una tomografía en muestras. Este es el tomógrafo, aquí hay una pequeña muestra muy chiquitilla de tejido, y entonces podemos obtener una reconstrucción en 3D de su estructura interna en una prueba que no es destructiva. Entonces esto es muy útil para justamente evaluar arquitectura de tejidos, ¿no? Sobre todo de matriz extracelular. Entonces, además de eso, se puede hacer fabricación. Entonces, como les decía, tenemos muchos métodos de fabricación, desde escala nanométrica hasta mesoescala. Entonces, tenemos la posibilidad de fabricar pequeños equipos de laboratorio, como en este caso es una bomba de jeringa, pero también hemos hecho bioreactores, agitadores de tubos, hemos reparado equipo viejo, que también podemos hacerlo sin mucho problema. Tenemos métodos más o menos sencillos, que son como el corte y grabado láser o un plotter de corte que nos permite estructurar plásticos y membranas como nosotros necesitemos. Tenemos maquinado CNC que nos permite hacer moldes como el que se muestra acá. Esos moldes después los podemos utilizar para hacer litografía suave, replicando las estructuras con silicones. Y también podemos generar películas delgadas poliméricas o de metales. Entonces, todo esto nos lleva a poder hacer plataformas como los órganos de chip. Aquí tenemos algunos ejemplos. Este específicamente es un chip de crecimiento, más bien de cocultivo, en donde se tiene un canal de color azul y un canal de color amarillo, como se puede ver en la imagen. Son independientes, pero están separados por una membrana porosa, entonces puede haber comunicación entre los dos canales sin que haya una mezcla de los líquidos. Entonces esto nos permite hacer modelos de epitelio endotelio de manera relativamente sencilla. Estamos trabajando en este otro, que lo van a presentar más tarde, que es la misma idea, pero en vez de tenerlos uno encima del otro, los tenemos uno al lado del otro, lo cual nos permite muchas otras técnicas de imagenología que no nos permitía el anterior. Tenemos chips como este que está aquí, este es de crecimiento axonal, no se alcanza a ver tan bien por el contraste que tenemos en la pantalla, pero es un chip que tiene dos canales, uno abajo y uno arriba, y entre ellos están conectados por microcanales muy chiquititos, tan chiquitos que no caben las células en esos canales. Entonces no hay migración de células entre canales, pero es suficientemente grande para ver el crecimiento de un axón. Entonces se ponen células de un lado, un quimioatrayente del otro lado, y eso genera el crecimiento axonal, lo cual podemos observar con este tipo de plataformas. Entonces, quizás no lo saben, pero nosotros hacemos un seminario quincenal en donde damos una pequeña plática de alrededor de media hora de alguno de los desarrollos que se está haciendo dentro del laboratorio. Entonces aquí hay algunos ejemplos de lo que se ha hecho en ese sentido. La otra es la unidad de imagenología cuantitativa, que nos permite utilizar todas las capacidades de microscopía del laboratorio. Estas imágenes son de epifluorescencia y esta es de confocal. Esta es una reconstrucción en 3D de me parece que es una espora un polen de planta. Entonces están muy bonitos, se tienen muchas técnicas de microscopía, además del servicio de preparación de muestras. También está la capacitación en el uso de diferentes tipos de microscopios y claramente se da mucha docencia dentro de este. Ahora, esto no tengo los videos aquí en este momento, pero una de las cosas maravillosas de la unidad es que no solamente es la cuestión de tomar las fotos, sino que permite hacer muchas otras cosas como este en particular son registros. Entonces aquí hay un ratoncito, este ratoncito tiene implantada una cámara en la cabeza, el ratoncito está en libre movimiento y mientras puede ver estímulos al ratoncito, se puede ver la actividad de alguna parte del cerebro en un registro de calcio de manera en vivo, digamos, ¿no? En vivo en el sentido más literal de la palabra. También se puede hacer en cortes histológicos, ese mismo registro. Aquí hay un corte de corazón. Lo que es maravilloso es que se pueden dar estímulos. Entonces tiene una cámara de perfusión en la que se está dando diferentes estímulos y se observa cuál es la respuesta a esos diferentes estímulos. Aquí están los videos. Ahí está el ratoncito moviéndose de un lado y del otro lado es el registro que se está obteniendo de las células que se ve con este microscopio, que se llama miniscope. Este es muy interesante porque permite hacer experimentos muy divertidos que antes no se podían hacer. Entonces, bueno, está la parte de docencia, que me la voy a saltar. Como les decía, de las imágenes que se han tomado en la unidad, han tenido la calidad para poder aparecer en portadas de algunas revistas, lo cual estamos muy orgullosos de. También la unidad de imagenología cuantitativa ha participado en los seminarios quincenales. Por último, vamos a ver la UNIBIM, que es la unidad de biología molecular, en donde se tienen todos los análisis que hay de ácidos nucleicos o de proteínas. También hay muchas cosas de inmunoreconocimiento, se pueden desarrollar un montón de cosas, se puede hacer monitoreo de crecimiento celular también dentro de la unidad y se pueden masificar los servicios. Entonces, como constancia de eso es que estuvimos dando el servicio de detección de SARS-CoV-2 durante la pandemia. Llegamos a hacer hasta 42,000 muestras en ese periodo, con un pico máximo de 900 muestras en un solo día. Entonces, ahorita estamos trabajando en BPH, como les había dicho, pero también estamos trabajando en detectar ciertos marcadores de cáncer. hemos participado también mucho en los seminarios quincenales. Estas infografías las pueden revisar en la página de internet si gustan revisarlas. Como decía, esta es la forma en la que trabajamos. Eh, Ahora tenemos algunos, digamos, desarrollos más grandes que involucran a todas las unidades, como lo puede ser este, que es una máquina de transporte de órganos. No es que no existan, ya existen algunas. En México solo hay una y es prohibitivamente cara porque los insumos son sumamente caros. Entonces lo que estamos buscando hacer es una alternativa nacional y accesible para esta tecnología, la cual es sumamente útil porque permite tomar mejores decisiones en cuanto al trasplante de órganos para limitar el desperdicio, digamos, de órganos, ¿no? Otra cosa que hemos estado desarrollando con el Conde de Valenciana es una lámpara para un tratamiento antimicótico de infecciones en el ojo. Son sumamente difíciles de atacar los hongos en el ojo. Para las bacterias hay bastantes antibióticos que son muy efectivos, pero para los hongos no tanto. Entonces se descubrió un tinte que se llama rosa de Bengala, que al ser estimulado con luz verde, produce radicales libres que son sumamente tóxicos para los hongos, en general para todas las cosas vivas, pero para los hongos, y no es particularmente dañino para para el ojo, ¿no? Entonces les ayudamos a desarrollar la lamparita que permite iluminar un área específica con una dosis específica y así poder hacer este tratamiento aquí mismo. Entonces, otra de las cosas muy interesantes con las que hemos trabajado es el desarrollo de una válvula de tratamiento de glaucoma, em, que estamos trabajando en conjunto con Marcoptic, que son quienes patentaron el diseño, y con el Conde de Valenciana, que nos ha ayudado un poco en el desarrollo de esta válvula. Es un desarrollo muy interesante porque es una válvula verdaderamente pequeña, tiene 1 milímetro de alto y 300 micras de diámetro. Es muy chiquito. Una de las ventajas de esto es que cuando inevitablemente se genere la película que lo envuelva y ya no funcione, se puede retirar y esa herida es perfectamente, el ojo es perfectamente capaz de cerrarla, entonces se puede volver a insertar otra, ¿no? Entonces hemos trabajado ya durante varios años con ellos en el desarrollo de este trabajo y ya estamos haciendo pruebas en animales, lo cual nos parece muy, muy emocionante. Entonces, el último y quizás el más desarrollado que tenemos hasta el momento es el desarrollo de un biosensor. Es una tecnología que se patentó en la facultad desde el 2016 y hemos estado desarrollándola desde entonces. Es un principio de funcionamiento muy sencillo, un cartucho con líquidos en el que se coloca una muestra, se pone en un dispositivo de lectura y se obtienen resultados muy rápidamente de una cantidad muy grande de proteínas y ácidos nucleicos distintos. Entonces, por ejemplo, ahí están algunos de los marcadores que hemos estado trabajando y el avance en las TRLs, que es la escala de, no sé cómo decirlo en español, pero digamos de desarrollo de tecnología que desarrolló la NASA para evaluar tecnologías entre su concepción hasta su comercialización, ¿no? Entonces estamos más o menos a la mitad, esto se está empujando mucho, es una de las cosas por las que se creó el laboratorio para empujar desarrollos que salieran de la universidad a un producto accesible para el público en general. Entonces, por este mismo desarrollo hemos obtenido muchos premios, todos han sido del lado académico. Em, ya no está. Bueno, y por eso creamos una empresa a través de la cual estamos sacando este desarrollo para poder, digamos que, llevarlo a lo que nosotros queríamos, que es un producto utilizable. Y bueno, eso es todo. Muchas gracias. No sé si ya se conectó el siguiente. ¿No? Ok. No sé si alguien tenga alguna pregunta, duda, comentario. Sí, claro. ¿Puedes, puedes poner este también? Cuidado. Gracias. Gracias.
Nada más mi duda es si cuando estuvieron ofreciendo los servicios de diagnóstico aquí en la pandemia para el SARS-CoV-2, ¿ya estaban usando la plataforma esta que están desarrollando microfluídica o era con una plataforma más convencional?
Este, el servicio siempre lo dimos con el resultado de PCR, pero como parte de un estudio para evaluar justamente el desempeño de nuestra tecnología. Entonces, salió primero porque decidimos, el desarrollo que habíamos estado haciendo lo había llevado la doctora Tatiana, se dedica a la neuroendocrinología, entonces había estado sobre todo enfocado en la detección de hormonas, empezando por insulina, pero pasando por hormona de crecimiento, de tiroides y demás, ¿no? Entonces, eso es lo que llevábamos desarrollado. Em, Cuando pega la pandemia, se decide ir hacia la detección del virus, se adapta el sensor en alrededor de 3, 4 meses y después de eso queríamos hacer una validación. Para la validación se necesita pues medir muchas muestras. Intentamos hacer colaboración con muchos grupos, pero era tanta la demanda de pruebas que era sumamente difícil obtener datos de calidad y bien controlados de otras fuentes en ese momento. Entonces decidimos implementar la técnica de PCR también nosotros en el laboratorio para poder hacer la relación directa. Y al tener la capacidad de hacerlo, pues empezamos a ofrecerlo al público y pues funcionó muy bien. Antes de eso, pues sí, ya teníamos la plataforma. Después de eso, empezamos a, digamos que le dedicamos más recursos, tiempo y esfuerzo a ese desarrollo. Entonces avanzó muchísimo más rápido, pero las bases ya las teníamos antes de, y después de eso, pues nos ayudó a empujar muchísimo más adelante la tecnología y desarrollarla mucho más. ¿Alguien más? ¿No?
Yo tengo una pregunta. La foto del ojo de la válvula, ¿de qué es ese ojo?
Es un ojo de cerdo,
Ah, ok.
sí, que literalmente sacamos de la carnicería. Entonces, pero bueno, fue muy interesante para justamente poder evaluar la fisiología del ojo y la posición correcta para la inserción, probar diferentes métodos, ver si la resistencia del material era la suficiente para que se quedara, si la metodología diseñada para la inserción era la correcta. Y como lo trabajamos junto con el conde de Valenciana, pues hubo mucha retroalimentación de parte de los propios oftalmólogos y médicos cirujanos que podían hacer este procedimiento acerca de cuál era la mejor manera de modificar ese procedimiento. Entonces fue muy valioso
Sí, sí, sí.
esa retroalimentación que pudimos obtener a partir de este ojito.
Ok. Eh, y la idea de la válvula es que no me queda por completo claro. Es que se quede insertada en el ojo, entonces, como todo el tiempo y que constantemente esté drenando.
Así es. La idea es, se parece mucho a una válvula de admisión de combustible de un carro. Entonces tiene un cuerpo externo, que es donde se ven aquí estos como púas, y un cuerpo interno que parece una jeringa. Es básicamente la punta de una jeringa. Y esos dos están unidos por un resorte. Entonces, cuando el resorte se comprime, la parte que es como una jeringa sale por acá de este lado y permite la salida del líquido. Eh, Cuando la presión baja lo suficiente, entonces el resorte regresa esto a la posición cerrada, en donde no hay ninguna salida de líquido, y se mantiene el líquido dentro, evitando que se apachurre
Ok.
el, el ojo. Entonces esto fue muy interesante porque pues tuvimos que trabajar mucho con el material, con la geometría del resorte y con el método para precomprimir el resorte a la presión correcta, que es otra de las ventajas que tiene esto, que en principio nos permitiría hacer válvulas que tuvieran una presión de activación distinta entre ellas, ¿no? Entonces podemos hacer una que tenga una presión muy alta, una presión media, una presión baja, y esto es una gran ventaja sobre lo que existe actualmente en el mercado para este tipo de dispositivos.
Ok, muchas gracias, Diego.
Gracias. Bueno.
Gracias. Oye, creo que una de las cosas más importantes es justamente este objetivo de que lo que se genera en la academia tenga un efecto en la sociedad. Eso está es de las cosas que más comparto, creo. Pero, ¿tú en dónde dirías que está el punto de inflexión o en dónde está ese cuello de botella para que todos los desarrollos que se generan en la academia puedan llegar eventualmente a que en las sociedades tenga un efecto?
Sí, ahí es un problema muy importante. En la universidad generalmente los desarrollos quedan entre el TRL2 y el TRL4, que es, digamos, el desarrollo básico de la idea hasta la generación de una prueba de concepto. Entonces, ese es como el alcance que tiene la universidad generalmente. Y la barrera más grande es estos de en medio, entre el 4 y el 6, porque esos son en donde se prueba la tecnología en condiciones relevantes. Entonces es donde se busca ver si efectivamente en las condiciones en las que se espera que funcione, funciona como se espera que funcione. Esa parte es cara, porque se tienen que adaptar métodos de fabricación para que parezcan a los métodos de fabricación final, entonces no puede ser una fabricación artesanal, tiene que haber más regulación, ese es otro punto, que hay una cierta alineación con regulación, específicamente para dispositivos médicos es algo muy relevante, eh, y es una formación que es, digamos, relativamente pobre en la universidad, sobre todo para quienes se dedican a ciencia básica. Eh, que es justamente toda esta regulación que tienen que cumplir los dispositivos para asegurarnos de que cuando alguien los compre en una tienda, vayan a hacer lo que dicen que tienen que hacer y que sean seguros y que no haya ningún problema en ese sentido, ¿no? Entonces, bueno, generalmente lo que se espera es que llegue la inversión privada a la universidad a decir, oh, qué cosas interesantes han desarrollado y decir, ok, yo compro esa tecnología y yo la llevo al mercado. El problema es que como este paso es muy caro y generalmente estos no se hacen con la calidad necesaria, cuando llega alguien interesado, se tiene que rehacer mucho del trabajo. Entonces resulta algo muy riesgoso para quien pone el dinero. Entonces lo que nosotros buscamos es poder ser un puente en este espacio para madurar lo suficiente la tecnología como para dar certidumbre a una posible inversión, entonces que haya más posibilidades de una inversión privada. Y justamente ayudar a la universidad a acercar su desarrollo a esa inversión privada, como para poder generar el puente que es necesario para que llegue ahí. Entonces, en otros países, como en Estados Unidos o en Europa, hay muchos programas gubernamentales que incuban proyectos. Entonces, eso es justamente lo que ayudan. Ayudan en ese punto 5 y 6, en donde dan inversión a fondo perdido, es decir, no te piden un regreso de esa inversión para que se desarrolle esa tecnología, ¿no? Casi siempre va acompañado con consultoría para asegurarse de que se está ocupando de la mejor manera el dinero. Y entonces, bueno, también ya la misma inversión privada sabe que de ahí vienen cosas interesantes, mucho más robustas, mucho más seguras, y entonces hay un buen ecosistema en ese sentido, ¿no? Entonces aquí se está empezando a empujar ese ecosistema en temas específicamente de salud. Ahí estaba, por ahí estaba el logo del IT Salud, que justamente busca impulsar mucho esto. Entonces ahorita está empezando, digamos, pero creo que pronto vamos a tener más de este tipo de desarrollos por acá.
Gracias.
Ah, perfecto. Pues creo que ya llegó el siguiente ponente.
Sí, creo que ya.
Muy bien, muchas gracias.
Bueno, nuestro siguiente ponente es el doctor Daniel Riverline. El doctor Daniel Riverline es director de investigación en el Centro Nacional de Investigación Científica de Francia y es líder del grupo de genética y biología molecular y celular de la Universidad de Estrasburgo. Es físico experimental y su trabajo se centra en los fenómenos de autoorganización en la materia viva, combinando física y biología cuantitativa. Entre sus contribuciones más destacadas están el descubrimiento de la mecanosensibilidad en contactos celulares y una nueva forma de migración celular, la rachetaxis, la cual es relevante para el estudio y el desarrollo del cáncer. El estudio del desarrollo del cáncer. Y bueno, pues los dejo con el doctor Riverline. Muchas gracias, doctor, por acompañarnos hoy.
Thank you very much for hosting me. Can you hear me? You can hear me
Thank you
correctly?
so much, doctor, for being here with us today. And
Thank you. In fact, I think I heard you. I just wanted to make sure that you could hear me smoothly.
we cannot hear you right now. I'm not sure if
Okay.
your microphone is on.
The microphone is on. My mic is on. Let me check again, but in principle, yeah, I can see that the Zoom is taking over. So I think, can you hear me okay now?
No,
You cannot hear me?
sorry.
I can speak and then you should hear me. Can you hear me? I can see that there is some signal from my side.
Sorry, I think we can hear you now.
Okay, can you hear me now?
Thank you. Yes, yes.
Okay, very good. Thank you very much for the kind introduction. And believe me, I wish I could be with you physically present, first of all, in this outstanding organization for the symposium. I saw the program and really I would like to attend it in Mexico itself. Unfortunately, I was teaching these days, and so it was not possible for me to come and attend. And I really look forward for other opportunities, either to go and visit you or you vice versa, to come in France and visit Strasbourg, where I'm sitting now. I want to thank, obviously, also both Tatiana and Pierre-Henri for giving me the opportunity to present our work. And I hope that, you know, after I have presented, there will be some interaction in a sense that probably I will be sharing ideas that you've been hearing in the past days, today and yesterday, and having feedbacks about what you think about our work would be really very important for me, and I will share with all the team members and the collaborators. So I'm starting now. I will put full screen. If you could tell me if you can see now full screen. It's okay? Good. So I think, and the sound is smooth and continuous. Right. Stop me at any time if there is something unclear or if the communication is not as smooth as it should be via the Zoom. So, in fact, what we are working on is about symmetry breaking and collective effect in biological physics. And what we try to stare at is essentially any phenomenon that would break the symmetry. So I think in the symposium, you have different backgrounds. And in this context, I wanted to give some introductory slides to set the stage in the type of phenomena we are trying to tackling. So if I define the word symmetry breaking, you have an object that is isotropic. So everything is in equiprobrable. So basically it's a sphere, or it's a disk, or it's a motion that is equiprobably right or left. And collective effect refers to the fact that somehow the addition of phenomena is not the sum of individual behavior. And for those of you who were not exposed to this concept, it's very intuitive. Collective effect refers to the fact that if you are in the train and if you are not many people inside the train, when you enter the train, you will look for seats and you will take the seats that you want. And I think as we all do, we will try to be as far as possible of another person. So basically, there will be an optimization of being alone and not too close to other people. In contrast, if we are in a train on a wagon that is fully packed, basically our motion will not be directed by what we want to do, but primarily by the crowd that is moving. If I have somebody in front of me that moves and somebody behind me, I'll be moving not because I want, but because I have to. So this is an illustration of a collective effect, if you wish. It's a crowd effect where all of a sudden, I'm not moving in the train as I want, but as a group, the group is going to move. And basically, symmetry breaking and collective effects are two keywords which have been playing a key role in physics in general. And what we'll try to present to you is that it's particularly important in biological physics because it gives non-intuitive phenomena. It's the addition of single elements which are not the sum of individual elements. And I'll be turning around this theme again and again and again. So again, for those of you who are not familiar with this type of concept, I will present a very simple scheme for that. It's taken from Anderson and his article from 1972. There was recently a Current Biology special issue about quantitative biology and interface with physics. And there are different people who wrote in it. And in particular, there is one article which is celebrating this article of Anderson because it's really inspiring. It was written in 1972, and he was postulating that broken symmetry and the nature of hierarchical structure of science is a key way of thinking about science in general, and biology in particular. Probably many of you know this paper. I want to highlight some features of this paper, just a few sentences. One of them is appearing on the screen now. Anderson writes, he was a Nobel Prize winner in physics. He's writing, by symmetry, we mean the existence of different viewpoints from which the system appears the same. So basically, you turn around the system, whatever, it's always the same. And then he postulates it's only slightly overstating the case to say that physics is the study of symmetry. And for those of you who are physicists in the audience, you all know that when you start Physics 101, you have to go through symmetry arguments. Or when you write different types of Landau energy, you have to go through symmetry arguments. So symmetry is really at the core. So that's one aspect. And the other aspect that he defends, and that he has very nice way of formulating it, he says, well, there is a tendency, that is, it seems to me that one may array the science roughly linearly in a hierarchy according to the idea. The elementary entities of science X obey the laws of science Y. So maybe I can skip the first one, but the bottom one will be, I think, here very meaningful. It's still tempting to say the elementary entities of chemistry obey the laws of science, maybe body physics, or the elementary entities of molecular biology obeys the laws of chemistry. And indeed, when we think about molecular biology, having a very good knowledge in chemistry is very meaningful. But then there is also a trend to say the elementary entities of cell biology obey the laws of molecular biology, which is also a trend, I think primarily vocally advocated by the community of cell biology for excellent reason. But then he proceeds to say, this hierarchy does not imply that science X is just apply Y. And this is where we're trying with many physicists around the world, actually, to give some contribution. Basically, it's not only the application, cell biology is not only the application of molecular biology. At each stage, entirely new laws, concepts, and generalizations are necessary, requiring inspiration and creativity to just as degree, to as great as degree as in the previous one. If I formulate with simpler words, it's a way of saying that, okay, if I am the scale of molecular biology, the nanometer scale, and if I want to translate this into a phenomenon inside the cell, I'm changing scale. And it's not only the application of molecular biology. One has to go through new concepts, creativity. And somehow, that's how Anderson postulates that whenever you change scale, you are bound to be seeing collective effects, an assembly of many molecules acting in concert in a condensate or in a macromolecular assembly. And it cannot be the sum of the individual entity. It might, but there is a low chance that it will be the same. Think about the crowd inside the train, right? Each entity will not move autonomously. It will be a collective effect that will show up. So I invite, for those of you who don't know this article yet, to read it in detail. It's extremely inspiring. And basically that postulates in a very eloquent way that, one has to think differently, the cell, the developmental system, by different eyes in good synergy with the true molecular biologist, and it is in this between that something can happen. So for those of you who are not yet convinced, actually, with this metaphor with the train, or I show you here a very nice movie that is not from me, that I took from the internet, of mass sheep herding. You can view it on YouTube. What you see here as individual animal, and you can see that when they move as a whole, their motion is essentially piloted with the density. Whenever they move, you have some lines which are parallel. There is, at the back, there is some dogs which are putting boundary condition. Here also there is a bottleneck so that they're getting denser. There is a broken symmetry that is going up front, and you can see some lines of coherence. Here you have a kind of vortex. At the end, you have some of them which are going faster than in the middle. And as a whole, they behave collectively in a way that looks like very different from what individual sheep would be doing. So the point is to say, we can treat single cell motion, or we can treat morphogenesis of an ensemble of an epithelial cell in the same way. For the cell motion, it will be treating each focal contact as a sheep, if you wish, and an ensemble of focal contact leading to cell motion. And for morphogenesis of a monolayer or epithelial monolayer, it will be saying that the individual entity is the cell, and the monolayer is basically the ensemble of cells that are behaving differently because they behave as a group. So unfortunately, I'm not in the room, and in that stage, if I were in the room, I would ask you to, interject, but it's a bit difficult because you're very small on the camera. I'll move forward, and then at the end, I'll try to stop ahead of time so that you can, react, debate, and so on. So I invite you to read, if you haven't done so already, it's Hydrodynamics of Matter, which is a review of modern physics written by key players in theory about the physics associated to it. And the interesting feature is that what's true for sheep will be true also for an ensemble of cells. So that's for the motivation. Broken symmetry on the one hand, collective effect on the other, and the merging point between the two, and the postulate that one should create new concepts to be able to capture the phenomena. So I'm showing you now how I'm going to describe the cell. This is an NIH83 cell. The time is in hours and minutes. And you see that during 24 hours, the cell that is on the surface is migrating straight, turning, migrating straight, and so on, turning. And the whole movie shows that the cell is crawling inside the surface in a random, persistent way. It's not totally random. There are some persistent motion, but also there is part which is random. Behind the cell, you must have been hearing very much since the beginning of the symposium of factomyosin. You have here stress fiber, which are labeled in green, and at the end of stress fiber, you have focal adhesion point, which are point of adhesion, which are in orange. So you can view the cell as a skeleton of factomyosin spread on the surface and applying traction force inward for the cell. So each of the yellow, orange points, you can view them as if my arm is the actomyosin, it's pulling on the surface and pulling inward. The dynamics looks like this. So you see the focal contacts, which are nucleated at the surrounding of the cell. And then as a whole, the cell is moving during this movie. This is only an hour and a half. If I play it one more time, you see that, focal contacts are growing, they are shrinking, they are growing again, they are shrinking. And one can have an intuition that somehow, as a whole, the focal contact is going to pilot the force distribution in such a way that the whole cell will be moving. You can probably guess that this is where my collective effect is going to show up. So basically, single focal contacts will be the individual entity, and I'll try to convince you that as a whole, they're going to behave differently. I need to introduce also for the presentation the other system that I'll be presenting today, which is MDCK epithelial monolayer that other speakers have been talking about since the beginning of the symposium, I believe. And here, this is a single cell here with the neighboring cell. This is E-cadherin that is stained here, and that's the other player. In the story that I'll be talking about changing shape in monolayer, the individual entity is the cell here, and the collective effect will be coming from all the cells that are glued to each other via adherent junction. To show you the dynamics, I've been borrowing a movie from Thomas Le Cuilab in Drosophila. Before it was MDCK in culture, epithelial cells. This is also now an in Drosophila, and you can see here that this system is extremely dynamics. In a dynamics which rings a bell with the dynamics of the single cell motion, right? You have actomyosin here, which is pulsating inside in green and pulling on the contact that are in orange, so the extrapolation can be sustained. But interestingly, if you play, trying to adjust some key properties of the cell, you can reproduce many morphogenetic events. I'm using morphogenetic in a very loose way. It's a change of shape for an ensemble of cells, or it's a dynamic motion at, along the illustration of the herd, of the sheep herd. So I'll be talking in a minute, later in the second part of the talk, about a ring of cells that you can see here. These are MDCK cells. And we've been showing that essentially the ring could undergo a spontaneous rotation. Single cells do not. But whenever they are assembled around the ring of connected cells, we've been showing that they undergo rotation, spontaneous, and this rotation somehow is a collective effect, and we've been trying to understand where it was coming from. But the interesting point is that with the same MDCK cell, and this was another work from the lab, we've been showing that if you plate a disk of cell, which is here isotropic, symmetry, if we were following it over time, we saw that this disk of cell could become elongated as an ellipse. So it broke its symmetry spontaneously. And what we've been showing in this other work, that I won't be talking about too much, is that it was the nematic field, meaning the orientation, like the sheep I was talking about before, the elongation of the cell, that were a determinant of where eventually the disk of cell was getting transformed into an ellipse. If I play the movie to give you an intuition of what this is, you see lines here of cell of elongation, which eventually this flow is breaking the symmetry and the disk is getting transformed into an ellipse. So again, a collective effect of cell elongation that is propagating and then breaking the symmetry of the whole. And the third example that I won't describe, but I just want to highlight that with MDCK cells, you can really take any dynamics and control any dynamics. You can make some pulsation, which is appearing here. The cells are pulsating inward and outward, as you would see in a beating muscle. And if you tune the condition, you can also have a situation where a cell, essentially the cells are going to flow like a liquid. Like a liquid will flow actually on the surface, like a viscous fluid. What you have on the screen at the moment is always MDCK cells. So it is the very same epithelial cells that are taken as a paradigm for changing shape and flows. And if I summarize here, we've been showing that you can undergo rotation, you can spontaneous break symmetry to have a disk which is transforming in an ellipse, you can have pulsation, you can have flows. The only element that you need to master is the initial boundary condition and the physical rules leading to these dynamics. So I hope with this example, I've been convincing you that, in fact, collective effect, yes, they play a role, right? And they are often associated with a broken symmetry. In this example, everything was isotropic, and all of a sudden, something broke its symmetry. So for the sake of focusing of, to be consistent with the time, actually, I've been selecting two stories. I'll be giving a hint on the third story, which will be turning around the same theme. The first story will be about single cell motion, and the story number 2 and 3 will be talking about rotation, spontaneous rotation of an ensemble of cells. So these are the title of the stories. Collective dynamics of focal adhesion, regulate direction of cell motion. The second story will be spontaneous rotation in epithelia as an interplay between cell polarity and boundaries. And the story number 2 will be polarity-driven, three-dimensional spontaneous rotation of a cell doublet. I want to give credit to all the co-authors and also give you the references. So the first story was the PhD of Simon Lovecchio in close collaboration with Laurent Navoret and Raphaël Voiturier. The second story, it was published in Cell System. The second story was Simon Lovecchio in close collaboration with Laurent Navoret, mathematician, Masha Chopos, Olivier Perse, and it was published this year in Nature Physics. And the third story was a close collaboration with Guillaume Salbreux in Geneva, and that was the PhD of Inji Lu and Tristan Guillaumard, and again in close collaboration with Olivier Perse. These two stories, story 2 and 3, are distinct, actually, but you will see that they go along the same type of reasoning. So let me start by the story number 1. Story number 1 goes like this. How can you have a cell going from a point A to a point B? So we are all used to chemotaxis, where the chemical compound somewhere is going to make a cell move directionally towards another point. This is not what we were chasing. We were wondering whether we could break the symmetry of a cell going from a point A to a point B in the absence of long-range broken symmetry. So I'm showing you again the single cell motion. And basically, I'm just recalling that you have focal contacts forming all around the cell and eventually getting self-organized and transmitting forth to the surface so that eventually a motion is possible. So if I say now the setup we've been using, I think in the introduction, even though my Spanish, I should improve my Spanish actually, but I understood that you talked about ratchet axis. And so somehow that's what we're trying to show, is that you can have a cell motion in the absence of long-range chemical gradients. And for this, we microcontact printing the surface with fibronectin that you see now in red. So the cell here is spread on the surface, and you see here the nucleus, and I hope you can see on the screen you have retrograde flow. This is DIC imaging, and the cell is spread, and everything is passivated everywhere else. So basically, you have a cell that is sticking to the fibronectin surface. So the question comes now, imagine I'm preparing different spots of fibronectin which are red, and I have the cell in the center, and I let the movie run for 2 days. The cell is in the center. I don't know if there is some mic in the room, but I want to ask you the question somehow. Where do you think that the cell will be moving? Probably there is no mic. I don't know if there is because you are muted. There is a mic or there is no mic? Yeah, the sound is off. Just to make sure that we are on the same page before I move forward. There is no sound, so I should continue or? Yes? Yeah, there is sound now, very good. So could you tell me where 1 or 2 people or 3 people, where do you think the cell is going to go if I play the movie? Any answer is well taken. Anyone? The one who has the mic, maybe. Where will the cell go? So it is visual. I see people making some gestures, so I can guess from the gestures. Any guess? Anyone want to give only one answer, maybe? Okay, I see a sign. The image is very small on my screen, but it is this. So basically, you mean it will go to the right, right? Okay. Your mic is off again. So, okay, if anyone has an ID, please show up and just tell me I'm wrong, and then, okay, good. So basically, usually when I ask this question, I have 3 answers. People will tell me it will go to the right. Other people, 4 answers, sorry. Some people will tell me on the right, tell me on the left. Otherwise, will tell me they will stay on the same spot. Let me show you the movie. The cell is protruding. It's trying to go to the right. It's trying to go to the left. And eventually, it goes back to the point where it was before. So in 2 days, the time is in hours and minutes, there has been somehow a probing of the cell that is trying to probe right, left, right, left, right, left, and eventually returning to the original point. So actually, for those of you who are the most theorists in training, you could argue, well, by symmetry, it's obvious, because somehow the broken symmetry is essentially on the line here, but it's not broken symmetry, it's a line instead of having all the space allowed. But somehow I haven't broken the symmetry really, because I have circle and that are organized inside the line. So basically we move forward and we wondered if we complexify a bit the problem by having triangle, triangle, triangle. And whenever I have the triangle, somehow you see that there is a front that has a large front and the back here that has a very small axis. And I'm asking the same question as before, according to you, I don't know if you have the mic now, but basically, where is the cell going to go? If somebody could try one answer, that would be great. Would it be moving to the right or moving to the left? And maybe I'll try to zoom, but I cannot zoom on the, yes? Oh, I see somebody talking.
Yes, to the left.
The left. So the left means when it is written L.
Yeah.
Right. Could you tell me why?
Do you wanna?
I just think it would go to the left because it has a bigger front, so the cell has more chances to find that other spot from the
Okay.
next triangle.
I agree with you, but for the sake of the scientific argument, I'll challenge what you said. Fine, I agree with you. There is a high chance to probe here, but there is a low chance to adhere. Because if I plot the intercept between the green and the red, which is fibronectin, there is a very small intercept. So even though the cell will be probing here, it will not be finding a fibronectin zone, so no chance to grow a focal contact. So then I'm challenging you by saying maybe you're right, but at the same time, you could be wrong. Somebody else want to try? A volunteer for the right. If anyone is thinking that the cell would go to the right.
Daniel,
Yes.
can you hear me?
Yes, I do.
I will go for the right for the reason you just evoked. That means that statistically you could find the area of adhesion, even if it's less at the beginning, you could build it more easily afterwards.
Okay, for the sake of science, I'll challenge you as well. I agree with you 100%, but in a way, I could counter-argue based on the argument of the former speaker in the room that here I have a low chance.
There's a technical problem on our side. The sound is no more jumping. So
oh, okay. Can
just
you
for a second, we are reconnecting everything. There was
okay.
Il y a eu un petit glitch de technique, on va dire.
Okay, can you hear me now? You tell me when I can continue.
It's ready. It's ready. We can hear you now.
Good. So I was trying to say actually that I agree with you, but I could try to argue that I have a low probability to probe here. I have certainly a high probability to adhere, but I have a low probability. So for the sake of a scientific argument, I could say that the former speaker in the room was having a point in saying that here there was a high probability to adhere, to probe, sorry. So basically, you see what I'm trying to get at. Here, on the one hand, I have a high probability to probe, a low probability to adhere. On the other, I have a low probability to probe and a high probability to adhere. So I'm somehow combining probabilities in a way that I don't know. So in such a case, one has to do the experiment. And this is what it looks like. So what you see here is the cell which is trying to go to the right, to the left. And you see the nucleus that is having this tug of war, right, right, left, right, left, right, left. Each time there is an arrow, the cell is trying. And eventually, Charlie was correct, but this is statistics. So the former speaker in the room was probably correct also for part of the event that we were chasing at. But somehow it makes the point that there is a possibility for the cell to eventually go to the direction that is not the direction that would have thought of because of the polarity, which is another argument usually that is given when I show this movie. That you could see you have a triangular cell, it's polarized, so the cell should keep its polarity, but that's wrong. It might, but it might not, because you need to transform a protrusion into a focal contact, which is not guaranteed. This example is easy. In a sense, you have triangle, rectangle, rectangle, high probability to probe, high probability to adhere on one hand, low probability to probe, high probability to adhere on the other. You see the nucleus dancing right, left, and eventually the cell, which is going to move to the left. So basically, based on this, we've been building ratchet axis in a sense of saying, well, you can have, if you let the cell run for a longer time period, you can have the cell that is going to rectify its motion. This was 10 years ago, where in fact, no need for long-range chemical gradient. The cell can move directionally in total absence of chemical gradient. So that set the stage, right? There is a way to control cell motion and to break the symmetry. It doesn't say the mechanism. So the story I'm going to talk about briefly here is somehow, how can we break the symmetry? And more specifically, before that, I was showing you essentially protrusion. I didn't show you focal contact, which is the place where the orange zones that on which the cell is pulling to eventually yield a motion. So the question we ask is, what are the mechanisms leading to rectification? Can the bias be increased? Can we predict direction of motion on different topologies? And the game was quite easy on the drawing. For Simo, it was a lot of work. If you take triangle, 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 and if you space the triangle to put them away, you can make the experiment, and now you're ready to go. You will repeat everything that I said before. You have a triangle that are spared, and then you try all the configuration, and you make sense of the quality of the rectification. So this is the type of data we generate, and I'll show you directly the results. The percentage of cell as a function of gap distance between a triangle. So obviously you have 50% if you have 25% overlap between the triangle. If you have 13, 16 micrometer, 19 micrometer, 20.5 micrometer, the rectification shows up. And whenever you are at 80%, you have, 22 micrometer, you have 80% rectification, meaning that all the cells are moving to this direction, so to the point, from the pointed end. So when Simo observed that, he came in the office and told me, it's strange, all the cells are moving in the same direction. There is something weird going on here. So we tried to dig in this direction, and with this, we teamed up with Raphael to have a fair way of quantifying all the steps. So what's represented here is, since you have a lattice with the triangle and the gap distance, this is a unit lattice, you call that a step. So step 1, step 2, step 3, plus is in one direction, minus in the other, and we want to be fair with all the trajectories, because distributed, there is some noise, the protrusion is not under control, there is some statistics in the protrusion. So P is the quality of the rectification, is the number of step plus minus the number of step minus over the sum of the number plus and minus, to be fair, because some cells are making 10 steps, others are making 5, others are making 20. So this is the mean bias per step as a function of gap distance, and you see that it is very nonlinear, meaning that, again, it's the same data as before. Before we took the last point and compared with the first point, here we take every single step to be fair with the whole trajectories of all events for 2 days. So we were puzzled by this nonlinearity. To go deeper into this, we wanted to have the focal contact themselves. So this is a VASP that some of you must be familiar with, which are protein of the focal contact. You see that the focal contacts are getting formed very quickly. As soon as the protrusion is being sent on the left here, the time is in minutes and seconds. You see that within 15 seconds, you have the focal contacts that are formed. This is on the left. On the right, the same story. Within 20 seconds or 30 seconds, you have the focal contacts that are getting formed. And if you still have some doubts, we use RICM, which is that was key in the 50s, 60s. At the time, it's still very useful to use RICM. It's an optical way of viewing focal contact. And you see that within 6 seconds, we see focal contact getting formed on the motif where there is fibronectin. So focal contacts are really getting formed. So I want to recall that we showed in the past that focal contacts are mechanosensor, meaning that when you pull on single focal contacts, they elongate and they recruit more focal adhesion protein. Intuitively, you can think about it as, when a cell is pulling on a single focal contact, instead of detaching, it's going to adhere better and apply more force. And we had quantified the force extension relation of this focal adhesion, which is 2.5 nanonewton micrometer. So you can view each focal contact as a spring. And in fact, if it is more elongated, the force applied by the cell is larger. So we built the next step based on this vision of focal contacts as if wish mechanosensor, but with a good spring constant, an unusual spring because it's adhering better if you pull on it, and it has the same amount of matter even if you pull on it. So we just take the 2.5 nanonewton per micrometer as a way to extract force without the need to make any measurement of force. I'm taking the length of the focal and I'm transforming that into a force. So now we have the cell line. You can see the focal contacts getting formed, and you see the distribution. So indeed, there is a correlation between the distribution of the focal and this famous first step that I was showing. To be sure that we were not fooling ourselves, we transformed the focal contact distribution here in force for each focal. So if I have a single focal here, I'm drawing a focal force here by the rule of 2.5 nanonewton per micrometer, and the force from focal are always inward because the stress fiber are always pulling inward. With this, I can have a force of every single point of every focal contact, and I have the total force. I can do this for the time at which the cell is jumping, and the third time point where the cell is dwelling on the neighboring motif, and I'm ending up with distribution of forces and the total force at each step. This is depicted now in the scheme that you see on the left-hand side. And what you can see actually is that on the y-axis, this axis, there is nothing interesting. The force is the same before the motion, at the motion, and after the motion. In contrast, along the x-axis, the force jumps for about 40 nanonewton up to 140 nanonewton and back to 40 nanonewton. So while the motion is happening, there is a jump in the total force. So we ask the question, is this force reasonable with what is known? So for this, we use the trick. If the cell is moving at a given velocity, if you know that at this scale, the force balance is given by F equal alpha V, meaning that the force equal the friction times its velocity. If you compute this number, you end up to 25 Newton second per meter, which is the typical friction that you expect that was measured by many groups. So we are on the safe ground. The focal contacts are the entities that are encoding the force, and as a whole, they're going to contribute to the motion in a key way. Good. Now we said so far so good. But there is a problem that somehow, if we are very intuitively reasoning, we should measure the interface between the protrusion area and the dwelling sites in the neighboring motif on the left and on the right. This is simple math. P is n plus minus n minus over n plus plus n minus, and this is going to be proportional somehow of a comparison of the area. It should be proportional to A plus, area of intercepts between the protrusion and the neighboring area, minus the same in the other side, over the sum of area. But if you do this, and this is what we did, it's desperately wrong. P as a function of the gap distance I was showing to you before is very nonlinear, and this relation between P and the area is linear. So we were wrong, but massively wrong. So we wonder where a mistake was coming from. So for this, we went to simple measurement, and we took the number of focal that a cell could generate in the neighboring motif as a function of area. This is depicted on the right-hand side. So we take the cell, we label them for paxillin, which is a protein of the focal contact, and we are, Simon did, measured focal contacts on the right, focal contact on the left. And we see the plot here. The mean number of focal contacts when the area is small is linear. This is the zoom here, the inset. This is linear, and after 8 focal contacts, it saturates. You cannot hope to have more focal contact than the cell can give you. And we said, haha, it might be the source of our mistake. So with Raphael, we went back to the math somehow, is what is the way to think about a saturating behavior? It's a tangent hyperbolic. So basically, we replaced the P that I was mentioning to you before, the mean step, by this expression, which instead of being linear, is a tangent hyperbolic of this A plus over A0, which is the critical area made by 8 focal contacts, minus the tangent hyperbolic A minus over A0 over the sum to be fair with all the trajectories. And you see here that now the fit is good. The fit is good, and on top of that, the only fitting parameter is the critical area, which is in the good range of what we had with the theory. So we were quite happy because it was somehow saying that, okay, there is a saturating area which could be the source of our error before, which should explain the rectification. So we sent the paper. We got 3 reviews. Referee number 1, great. Referee number 2, very good, but, and referee number 3, come back whenever you will have made the test. So of course we did the test, otherwise I would not be telling you about the story. And so basically a good C model should be having predicting power. So we said to convince the referee 3, what we should do with Simon is to design a motif and a gap distance that should be able to have a motion in the opposite direction. We would design the experiment before, predict the mean P, and then compare with the theory. So to be fair, the theory should predict the future experiment. We do the experiment, we compare. That's how physics should work, and that works usually. So we did the teardrop. That was the motif. Teardrop is a motif like this. So it's not the triangle as before. It's like a drop, but a drop with an asymmetry and a blunt end on the one hand. And Simon repeated all the experiments. So basically, you have here a certain gap distance, another gap distance, and to be safe, we also reproduced the experiment with triangle and the 22 micrometer, which was the point at which this was happening. This was the result for the triangle. This is the result for the teardrop. And you see here that indeed you have here the nonlinear increase for the triangle, and here the nonlinear increase for the teardrops, and isotropic for the triangle as expected. Here the symmetry is obvious. And if we compare our prediction with the experiment, you see that the experimental P and the theoretical P are matching for all the quantities. So somehow we had the predictive power, and that was setting the stage. So the paper was accepted. And then what we were explaining in the paper, which I'm going to summarize, is that what is this meaning of this 8 focal contact, this saturating behavior? I think you get the answer, is that this 8 focal contact is the collective effect. You need to reach this critical number of focal contacts somewhere in this tug of war to eventually have winning side, which eventually is going to polarize the cell and then perpetuate the memory of the polarity. And so that's the scheme that is summarizing the story. So basically, we had this ratchet axis effect that we had shown 10 years ago. And a few years ago, we have proposed, and I think we've been proving, that in fact the mechanism was the following. The cell is probing right and left. When it is reaching a critical number of focal, which is a collective effect of 8 focal contacts, there is a competition right and left. As soon as one is going over this saturating behavior, it wins it all, the cell gets polarized, and eventually will keep this polarity over time. And somehow that was the test that we did with the bias in the direction and the bias in the opposite direction with the teardrop. So I hope I convinced you that in fact this is an example of a collective effect in the broken symmetry. The single focal contacts, there is a force extension curve that is canonical, that is working, from which you can infer force. But as a collection, they're going to behave differently. And the new entity is 8 focal, 10 for some other cell it would be. But as a whole, they will behave differently. And then collectively, they're going to mediate with eventually how a cell will polarize and eventually perpetuate its motion. Is it okay? I cannot see you. That's very frustrating. I wish I were in the room with you, but so far so good.
Yes, thank you very much.
Oh, huh?
It's okay.
Okay, no.
It's okay?
Yes, thank you very much.
Can I move? Okay. Tell me how much time I have left to be good in time.
Like 10 minutes.
Okay, very good. So you tell me, if you wish, I can take question now and I can leave the rest of the talk for some other time, or I can stop earlier so that at what time, I know we started later on. You tell me what you prefer. I speak 10 minutes or we finish in 10 minutes?
We can go for some questions.
Okay. So maybe before you reach the question, Pierre-Henri, I just want to show the 2 other examples very shortly, so that then we go to the question, if it's okay with you.
No problem.
Because then that will just allow me to wrap up and to thank all the participants, which I haven't done. So the story number 2, I'll just show you the hint of it. It is the ring of cell I was mentioning to you before. I just want to show you what is the connection with the collective effect. If you take a big ring will not rotate. If you decrease the size of the ring of cell, it will not rotate yet. If you decrease the ring diameter, it will eventually rotate. And somehow in this phenomenon, what we've been studying somehow is how come the cell could rotate. So we've been observing the cell, tracking them over time. And to cut a long story short, what we've been showing is that the cell were having a tug of war of polarity. And if over a given coherent length, the cell were having all the polarity in the same direction, eventually they could rotate. And this was about 10 cells. So the reason I want to mention that is that you have a collective effect now, because it's not the single cell that is setting the stage. It is an ensemble of 10 cells, about 300 micrometer. If they are in the perimeter, in a ring, the only thing that they can do is to rotate. It's like a train with many wagons. They can only rotate in the same direction. So this is basically the story number 2 that I just want to highlight, if you wish. In spirit, it is very close to the story number 1, but here it's an ensemble of cells that undergo a rotation. And the final point I want to say on this story is that somehow all this is mediated by a tug of war between polarity. So I'm skipping gears here. I'm just showing you the snapshot of basically what the story is about. It's essentially a matter of competition between polarity of cell, which whenever they are in opposite direction, since the velocity and polarity are competing with each other, it's not rotating. Imagine you are all around a circle. Some of them are pulling clockwise, another counterclockwise. They will never rotate. And eventually, when this will be resolved over a coherent length, it will undergo rotation. That's what we've been showing experimentally in the paper that was published this year. We also probed it numerically, because for collective effect, we cannot wave our hands. We need to go through numerical simulation. And that's what you see here with particle. The particle have a velocity, they have a rule of velocity polarity, and eventually as a whole, they're going to undergo a rotation. So basically, this is the spirit of the story number 2, where now the individual element is the cell, and the ensemble of cells, when they resolve the tug of war, they eventually will undergo a rotation. So there was a test with the model, etc. I will skip to the very last slide for the acknowledgement, and then we'll take the question. Basically, okay, just one slide about the story number 3, I cannot resist. We had a rotation of doublets. Now we are in 3 dimensions. So all of them, this is mesmerizing. So all of them are rotating like this. And we're trying to understand, why are they spontaneously rotating inside the matrix they are 3D before the story was 2D? Same story, polarity. So what we've been chasing is that what is the mechanism of the polarity of the cell changing each other? And for those of you who are physicists in the audience, we've been proving that the Curie principle, which is a century-old principle, was verified in this system as well. So I will go to the last slide of acknowledgement, and then I'll take the question. So basically, you see the spirit of what we've been trying to show, essentially. It's a mixture of experiment, theory, and comparison between theory and experiment, and physiological relevant, because this type of rotation, you have it in vivo for Drosophila in the egg chamber, for the alveogenesis, also where also they undergo rotation. So it's not a pure game for physicists. It seems to be having also some implication in developmental biology. So the 3 stories, story number 1 on which I was dealing was an ensemble of focal yield a collective effect that eventually rectify the motion. The story number 2 is spontaneous rotation in a ring, and the story number 3, that I just alluded in one word, is the doublet rotating in 3 dimensions. But the main point I want to defend is that more is different, right? Ensemble of focal lead to a new phenomena, new creativity. Ensemble of cell lead to rotation in a new way that single cell would not be able to do. So the story number 1 was a collaboration, close collaboration with Raphaël Voiturier. And story number 2 and 3 were 2 with Laurent Navorret, essentially, Marcella Chopos in Strasbourg University, and story number 3 with Guillaume Salbreux from Geneva University, and you have the funding bodies in the right-hand side. And I thank you for your invitation and for giving me the opportunity to present.
Thank you so much.
Daniel, thank you for all of this, and thank you for being present. Sorry for the glitches. We are dealing with different technical issues here.
No problem.
I have a very naive questions. Whenever we play as physicists with the boundary condition, we play with the average of the boundary condition. How are the phenomena you just shown resistant to fluctuations or slight fluctuations of this boundary condition? That means how stable, how those symmetry breaking collective behaviors, you may have some extra rules or at least extra damping in the system to kill the fluctuation of position, interactions, and testing. In particular for the triangles, you shown a shape that is very asymmetrical.
Yes.
And I was wondering if you render the shape symmetrical, how it would be.
So, okay, thanks. Thank you. So I'll start by answering your question, not with the triangle, but with the ring. And I'll go back to the triangle very shortly. So I was presenting very shortly the story number 2, which is the ring that is undergoing a rotation, right? This is what I was showing with below a given dimension, you have a coherent length of cell that eventually undergo rotation. So in this case, actually, what is securing the quality of the rotation is the boundary condition, which we are not setting, but that the cell is setting itself. So I like your point, because it was very quick in what I was showing in one slide, but you have self-assembled actomyosin ring inside the ring and outside the ring that is imposing the boundary condition. It's not us. I mean, we are imposing the fibronectin ring so that the cells are organizing to ring, certainly. But apart from that, the cell itself is assembling an actomyosin ring outside and inside. So the boundary conditions are key. And more than that, we've been proving that true activity with Fred sensor was on. And mathematically, you need this contractility to eventually rectify the motion. So you get a key point in what your question was formulating, is that boundary conditions are essential. And I would argue that they are as essential as the dogs around the sheep herd, somehow. They are setting the stage of basically making sure that the overall symmetry imposed as initial condition is preserved over time. Now, returning to your question about boundary condition, in the context of the story number 1, which is the ratchet axis, which is the triangle. For this, I would be cautious. In a way, the cell has an initial boundary condition, but contrary to the story number 2, what we care about here is the cell reorganizing its own boundary vis-a-vis the neighboring motif. So the story is a bit different from, if you wish, only boundary conditions. The boundary conditions are going to be essential for time zero. Basically, we start recording whenever the cell is really having this triangular shape imposed. But then with the fluctuation and the attempt to attract right and left, this is going to be challenged. So that's a way of trying to argue that it is boundary condition at time zero where the triangle is totally full, which is essential. After that, we leave the system go, and eventually the cell will polarize in a direction that has nothing to what to say. And to answer now directly to your question, we change the motif. We had a circle, as you saw in the first guess. We also have, different shape of different type that I didn't present you today. And this boundary condition were essential to have the effect. So these are 3 elements of the answer. First point, cells themselves can make the boundary condition rigid over time so that you secure that there is not too much fluctuation out. And answer number 2 is that when you give this freedom of free boundary condition, what we need to secure in our effect is very strict boundary condition at time zero. Then we let the system go. Does it answer, Pierre?
Yes, thank you. I was also wondering if perturbating your thing using, for example, optogenetics, just slightly perturbating the boundary condition will lead, in that case, to a correction of the boundary condition first, then to the system to get into this symmetry breaking.
So I cannot resist because you asked me the question, right? So it is in the story number 2 that was published this year. We played with optogenetics. So you have a rotation, right? With basically the rotation I was showing to you before, right? So this is rotating. To cut a long story short, you have 2 clusters of myosin on both sides of the cell, which are somehow allowing the cell to rotate like this. This simple-minded, which we observe experimentally, hypothesis was substantiated by Guillaume Salbro and Quentin Vagne. When they have 2 cells interacting numerically with an active gel equation for the cortex, and they put hotspot of stress here, the cells undergo rotation, and there is here this very yin-yang shape, actually, which is appearing. And now returning to your point, we wanted to challenge boundary conditions by optogenetic tool, specifically raw optogenetic tool, to activate locally raw and to have a local myosin clusters. Because as I was saying, there were 2 myosin clusters here. What about an ectopic myosin cluster to, perturb the boundary condition? That's what we did here, and this is the movie at the bottom here. The optogenetic core is going to appear here. You're going to see a spot of myosin appearing, and then when we shave the line off, the spot is going to go out. And look what's happening. Rotation, on, down, and then rotation. So here we transform the rotation into a translation and back to a rotation. And if somehow we wanted to be sure that we're not fooling ourselves, we didn't change anything in the simulation. It's rotating. We have the hotspot of optogenetic row, and then it's recapitulating, goes back. So that reinforces your point that if we challenge the boundary condition that the cell sets by itself by optogenetic row that is going to make the boundary condition change because of stress generated somewhere else, indeed, this is going to change dramatically the direction. And this can be as subtle as a single point. Here it was a local point of myosin cluster generation. So I'm totally on the same page as you are. It's the boundary condition is one of the key elements in all these collective effects that I was mentioning. If you perturb them, you change the dynamics. Temporarily, I mean, you see here that it goes back actually, but if you are more persistent in the way you do it, you should expect actually a long-term effect. So boundary conditions are one of the key elements indeed.
Thank you. Is there any other question? Okay.
Thank you. Have you tried these experiments in which cells migrate through geometrical shapes, but with a large-scale culture? Because these experiments that you are showing are for a single isolated cell, but maybe with a larger scale culture, the cells will not behave the same way. Have you tried it?
So I'm going to repeat the question, and you tell me if I'm on the right track or the wrong track. What you're asking is that are you asking the question about single cell versus an ensemble of cell, or are you asking the question actually because I heard at the beginning of the sound was not very good that have we been challenging this ratchet axis with chemotaxis? Can you, is it question number one or question number two? Or maybe it's neither of the two, actually.
More into number one.
Okay, so the number one is basically if we have an ensemble of cells plated on this ratchet, do we have a global rectification? Basically,
Sorry,
the experiment would consist of plating MDCK cells on our ratchet and to see is as a whole, the colony is moving in one direction. This is what you are asking.
yeah, exactly. The experiment.
Okay, so this is a very good question. That was, it's a very good one. The short answer is no. They are not rectifying, right? And we've been trying hard because that was the obvious next step when we were doing proving the ratchet axis, right? And this is specifically what led us to, I was showing you the slide where in fact we said we are making a gross mistake. And I like a question because somehow what I was showing in the slide, maybe the best is that I go to this mode, actually, I go directly to the slide. You remember this introductory slide where I was telling you that, in fact, if you take an ensemble of cells, you can shape transform the way you want, right? You can have rotation, you can have elongation, you can have pulsation, you can have flows, yeah? So in a way, when we were doing the ratchet axis, the next step was to go to monolayer, and we were dramatically failing, right? We were very failing, and we didn't understand what was going on. It was poorly reproducible, and we didn't understand why. This was 10 years ago, I guess. And then we started to think maybe we make a gross mistake, which is that somehow the system itself at its own coherent length, embedded helix. And now we come back to this principle of coherent length. If you think about a epithelial layer, we cannot anymore think about single cell. It's not possible. What one has to think about is a train of cells, so 10 cells. And the 10 cell, 20 cell, it does depend on the epithelial layer. Somehow, it's now the 10 cell that is a new entity. And if you take the 10 cell as a whole, then you can start rectifying. I hope I cannot see your face now, so I'm not sure I'm making myself clear. But basically what I'm trying to say is that we tried, it failed. So it means that we were making a gross mistake. What was our mistake? That we were considering that single cell inside the monolayer is going to be trapped by a triangle. This is wrong. Essentially, you need to consider a larger scale, which is the scale of the coherent length, basically. Think about a train of cells that are behaving as a chain. And if you take that into account, now you can rectify, but you should change the motif dramatically. And the way to show that we succeeded is somehow this middle movie I was showing to you before, that now we have a rectification inside the circle. So no, it's not exactly the same, but somehow it's a rectification because the tug of war is rectified. But if you wish, it's exactly the point of a collective effect. That if you go from one cell to many, it's not the addition of the individual. There is a new system which is spontaneously appearing, which is the tennis shell new entity.
Okay.
Can you take back the mic to tell me if you got my point?
Yeah, actually, it was very, very well explained, the answer.
Okay,
Thank you so much.
Is there any other question? No? Well, thank you. Thank you again for this interesting presentation and insightful. Sorry again for all the technical issues that we have today.
No problem. It was smooth and easy, and I'm looking forward to meeting each of you some other time.
Yes, we're looking forward to it too. Thank you.
Bye.
Bye.
Bueno, esta es la última sesión del momento. Los invitamos a pasar a ver la sesión de pósters que está aquí afuera. Después tenemos el receso para la comida y regresamos acá con dos pláticas que van a ser presenciales, que espero que les gusten mucho. Y ok, eso es todo. Nos vemos. No olviden seguirnos en redes sociales. Están allá afuera los QRs, por favor. Ya. La ponemos en la compu. Sí. Está feito, pero no es que esté fuera de foco. No se escucha. ¿Los imanes los bajaron ustedes? ¿O no? Y están por ahí poniendo alguna.
¿De dónde está guardado su broma?
Bueno. ¿Tienen el collar? ¿O tienes los imanes? Sí, ¿no? Ahí está. No, no. ¿Son los clips? Son los otros. No, no te preocupes, con este. O sea, sí, con este. Por favor. Sí. Para que te escuches. Vale. ¿Así? ¿Entonces al revés? ¿Así está bien? ¿Sí? Pero-
Sí, pero ahí está prendida. Este y este. Ah, este que está pegado. Se despega así.
Y este sí. ¿Sabes qué? Olvídate.
¿Qué pasó?
Ahora sí, este. ¿En serio? Pero si ve bien la transmisión. La presentación sí se ve. Bueno,
Buenas tardes a todos los asistentes. El día de hoy nos acompaña el candidato doctor Nicolás Pérez, quien es estudiante de la doctora Eda Shuto, destacada investigadora científica e inmunóloga del Departamento de Inmunología del Instituto de Investigaciones Biomédicas. Su trabajo se centra principalmente en el estudio del efecto de la inflamación y la neuroinflamación en patologías inmunes. Adelante, Nicolás.
Sure. So thank you so much. Do you hear me? Yeah? Well, it's okay. Okay. Well, I will talk you about organs on a chip and specifically about a novel tool to study neuroinflammation that will be a blood-brain barrier on a chip. First of all, we need to talk about organs on a chip and in particular about biomimicry. Maybe you have seen these images in which we always see how nature inspires us to make some things. Eventually, we can take this knowledge to make some buildings, wherever. In the nature, we can have these specifically structures that allow us to build things that this stadium, but I will be more specific in the biomedicine, because all of these examples that you can see in those images are from the perspective of not biological science. And talking about what happened when biomimicry meets biomedicine, we can have these biomimetical or biomimetic models. In these ones, we can say, okay, thank you. In these ones, we can say that we can group them in three big areas that will be bioreactors associated with scaffolds, organoids, and organs on a chip. Bioreactors associated with scaffolds allow us to make these kind of things like some implants of ears, some implants of hearts, or maybe some tracheas. These ones has the specific function to replace a structure inside a body like a air or like a trachea. But they are not so useful to model pathologies or maybe model physiologically conditions. So the other biomimetic model that we will have here will be organoids. Maybe some of you have seen yet before, and in these images, we can see a rat cerebellar cortex histological section. You can see in this section how the structure is formed. You have a micro topography and a micro structure, very characteristic of this organ. So when you try to do a brain cortex organoid, you can see that organoids allow us to resemble how the microparticular structure of the organ is in nature. This is very useful to study some illnesses from the very beginning of the development. But I will put in the table very specifically the organs on a chip. And actually, I put this slide because I want to make like a conclusion all at the end of my presentation that will be the joint of these two strategies. But first of all, we have to talk about what is an organ on a chip. An organ on a chip is a strategy that aims to join the advantages of traditional in vitro and in vivo modeling. These advantages will be developed over a microfluidic device.
maybe in the practical sessions, you will see how these microfluidic devices are. So eventually, we can have organs on a chip developed in microfluidic devices, and there we can make the modeling of these different diseases or specific physiological conditions. And what we are looking for is to get closer to the human physiological context and reduce the animal usage of in vivo modeling. So I will now talk about biomimicry because it's the main point of this kind of models. Nevertheless, I want to emphasize that in organs on a chip, we can have different complexity. And actually, a very special feature of this kind of design of devices is that if you have a non-so-complex question, maybe you can use a non-so-complex organ on a chip or microfluidic device. But as your question gets complex, your device can be as complex as your questions. So you can have in here some interactions. These chips is used to see how neurons' axons grow from left to right after a stimuli, a chemical stimuli. But imagine that you use a new molecule to promote axonal growth. Then your question starts to get complex, and then you want to know what happened when you administrate this molecule that you know that allows axonal growth. What happened with this molecule when you administrate it through an intranasal route organ on a chip, then through a lung organ on a chip, and then with heart, kidney, liver, gut, and so on. So as you can see, when you have these new molecules, you can try them, you can test them in these multi-organ platforms. And what is more, you can have these organ platforms with some biosensors that allow you to test TEER, that will be transendothelial resistance, that will allow you to test some concentration of molecules that will be of your interest in vivo, you know. So all of this, for sure, have to be done after or with a very high characterization. As your model gets complex, then your characterization should be complex, as complex as your model. Why? Because you are aim to have a biomimetical model in your research. So the characterization is very important to establish this statement of the biomimicry. Tal vez. No. Tal vez como lo de la pantalla doble, ¿no? Ampliar pantalla y eso. Ya estoy aquí, ya estoy compartiendo. No me deja, yo no se ve. Vamos a cambiar eso.
Duplicar estas pantallas.
Ah, ya se ve. Sí, pero la pantalla no en presentación, en pantalla.
No se ve, no se ve.
O sea, sí se veía la presentación, pero no en modo presentación, estaba como en... Tal vez... Ay, no. Ahora estás compartiendo la... Ya, ya. Ok, ya no lo voy a patear. Sí. Okay, so from here we know that organs on a chip needs to be organs on a chip are as complex as your question is, so you can actually design them for your very special necessities. And as I said, you should characterize all your model to have a good and robust model of you whatever you are studying. So, how is a common organ on a chip setup? In a common organ on a chip setup, you will have these microfluidic devices. Every red and green channel in here are microfluidic channels that will allow you to interconnect organ on a chip 1, organ on a chip 2, and then you can have this peristaltic pump connected as well to all the microfluidic devices. The peristaltic pump is so important. So in the physiology, you can resemble the blood circulating using this peristaltic pump. This allows you to have physical shear stress to your cells. You can administrate something to the system using this peristaltic pump. And after all, you can have an extra chip that will be the one that allows you to have this analysis that I was talking about. Some molecules that cells were secreting maybe can be tested in this extra analyzing chip. But in the reality, maybe they can look like this with some special peristaltic bombs that allows you to have this kind of setup. It's very important to say that every compartment should be interconnected by tubing. The tubing is like the blood vessels in your body. And something important is that inside this particular setup, you can add well, at least theoretically, you can add whatever kind of chips that you want to make your research questions. So, what you can model on a chip? As you can see in this photograph, chips can be used to model almost every structure in the body, and not only organs, but structures inside organs. So all depends in what is your question. You can model administration route, maybe an oral administration route, maybe an intranasal, subcutaneous. You can model the brain, you can model the blood-brain barrier, you can model the liver, wherever. And as you can see, all of these designs are specific, all of them, they are different because they are specifically designed to accomplish the research questions for every one of these structures and organs. So you can study physiologically context, but you can also study pathological context. So one of the structures that actually can be modeled in a blood-brain barrier, and I can say that is one of the models that are like more simply designed but very useful, is the blood-brain barrier.
The blood-brain barrier is a structure inside the brain, inside the central nervous system, which main function is to modulate the flow of molecules and cells through the periphery to the central nervous system. It is composed by several different kinds of cells that will be neurons, astrocytes, microglia, pericytes, and mainly endothelial cells that will be the ones forming the blood vessel. Here we have another non-cellular component that will be the basal membrane, that is kind of the extracellular matrix component for this structure, and tight junctions that will be these little ones between endothelial cells. So all of these characteristics gives the function of the blood-brain barrier, and these characteristics will be modified when you are in a pathological context, when you are during the early born development, when you are aging, you're studying aging. So these functions will be dynamic and will respond to the physiological needs of the brain in every single specific moment. So, why to develop? Why we decide to develop and to look after a blood-brain barrier on a chip? For the past years, we have in our lab, we have studied the neuroinflammation associated with some neuropathologies. Some of them are stroke, multiple sclerosis, and Parkinson's disease, and sepsis. So, besides the results we have had, we have noticed that our therapeutical approach, that will be the administration of dexamethasone as an anti-inflammatory molecule, the intranasal administration of it is modulated by the blood-brain barrier. So, try to study how these molecules and some others interact with the blood-brain barrier is quite difficult if you have an in vivo model and you want to isolate the blood vessels from that in vivo model. So that's why we start to look after a new model that allows us to make some extra questions in the management of neuroinflammation after the administration of glucocorticoids like dexamethasone. So, what happens when a blood-brain barrier is attacked by neuroinflammation? You remember I said that basal membrane was like the extracellular matrix of the blood-brain barrier. So when inflammation occurs, this basal membrane gets diminished, and that allows to the pericytes and astrocytes disattach from the interaction with endothelial cells. After that, the tight junctions that are between endothelial cells start to get open, and after that, peripheral circulating cells can pass to the brain parenchyma, and some molecules like cytokines can activate astrocytes and microglia. So these two cells and pericytes as well can reinforce the pro-inflammatory environment of this neuroinflammation process. At the very end, you will have some neurological impairment, axonal damage, and myelin loss. So that will trigger the patient disability. This is the context that we are looking for to model in the blood-brain barrier on a chip. Of course, different neuropathologies have different context of this general process that I have described. So, not all the diseases can
trigger the same intensity of neuroinflammation nor the same effects on the cells. So, as I said, one of the diseases that can actually damage the blood-brain barrier is sepsis. This sepsis is it's a condition characterized by a multi-organ dysfunction derived from a peripheral infection. So these sepsis have like a variation of that will be cephalic sepsis. This cephalic sepsis is the main cause of patient disability. So that will be the one that we would like to study in this blood-brain barrier on a chip. To study the sepsis, the most common model will be to administrate LPS, that will be a component of bacteria, cellular wall, and stimulate with these LPS in vitro cells or animals like mice. So, having this in mind, we start to look after the development of this biomimetical model called blood-brain barrier on a chip. And the sepsis model allows us to induce the pro-inflammatory statement in a kind of simplistic way, because you only have to administrate the LPS in the cellular medium, culture medium, and then you will be stimulating for a pro-inflammatory process in your system. So from here on, I will tell you about our approaches to study neuroinflammation in an LPS-derived neuroinflammatory process on a blood-brain barrier on a chip. Our model. How is our model? We have this microfluidic device designed by Lance Biodit here in Science Faculty. So this microfluidic device will be in three parts. Upper channel, mid collagen 1 membrane, and lower channel. This will be like a sandwich. Imagine that the bread will be the upper and the lower channel, and then the collagen membrane will be like the jam or something. Then the collagen membrane, as you can see in here, is a transparent one. So it allows us to see all the cells that are cultured on it in whatever time we want. So as you can see in here, the design have inlets and outlets. These inlets and outlets allow us to introduce to the system whatever we want: culture media, chemical stimuli, shear stress medium with peristaltic bombs, whatever. And as you can see, the culture area will be this little square inside the chip that will be like 10 millimeters length, 2.5 millimeters wide, and mainly the main characteristic of this culture area will be that it is 200 micrometers tall. So imagine the amount of medium, the amount of reagents, and the amount of cells that you need to fill this area. It's very, very small amount of reagents and cells. So this characteristic allows you to put this device into almost every microscope in different labs. You do not need to put the device on a vertical or an inverted microscope, maybe a confocal. You can put it in almost every one of them, and then you can see the cells inside this device. That will be a very nice feature of this kind of design, because we can have the device, we can see what is happening with the cells from the very beginning that we seed them and in the time that we want. So this collagen membrane should be characterized, so we can think that this characterization, so this collagen membrane allows us to have cells seeded on it, and then to perform our studies. So we have characterized it, and we notice that is more or less 300 nanometers of the diameter of the fibers, as you can see in this photograph. So this is important because this will be a porous membrane that will allow the flow through one side to the other of the membrane of different things. Included the cell culture medium, for example, and molecules secreted by cells. So the thickness is about 4 micrometers, which allow it to be translucent, so we can see the cells inside over it. It have a Young's model of 84 kilopascals that will say us that cells can make their forces inside over this membrane and could attach to it in a very good way. And it have a roughness of 100 more or less nanometers. So with these characteristics, we were thinking that this membrane is a good option to culture cells on it. A very important thing is that cells can develop forces over the membrane. It has now, there is information that says us that if your surface is so stiff, maybe the cells, at least endothelial cells and the brain parenchyma cells, will not be so happy inside over this kind of stiff surfaces. And that will be because of the nature of the brain parenchyma. If you compare the brain parenchyma stiffness with the stiffness of maybe a lung or maybe a bone, they will be different. So cells can sense these differences and want the specific stiffness of their organ. And in this case, something that get closer to the brain characteristics. But after this characterization, there are some questions that we have to solve, because actually we can imagine that these characteristics allow us to culture cells over it, but we do not know if it will be helpful to develop the system. One of these questions will be, can it allow physical interaction between cells? That is an important question because remember the physiologically picture of the blood-brain barrier, in which endothelial cells, astrocytes, and pericytes are in a very straight contact. These three cells are a very, very close contact. So physiologically, this contact is needed to express the correct phenotype and function of the blood-brain barrier. Can it be useful for permeability tests? Now we know that this is a porous membrane, but we do not know how the different solutions will flow through it. And maybe the most important thing, can it be useful for develop a blood-brain barrier on a chip, even though this is an static model? I'm going to make a parenthesis because in the physiology, the blood flow is making some shear stress over endothelial cells. And this shear stress is important to develop the correct, fully phenotype and functionality of endothelium. So even though this is an static model with no peristatic bombs perfusing culture media inside the system, the question is if it will be useful to develop a blood-brain barrier model. To make this model happen, we use a co-culture of endothelial cells, astrocytes, pericytes, and microglia. Endothelial cells will be in one side of the membrane, and in the other side, astrocytes, pericytes, and the microglia. So this will be the vascular part of the model, and this will be the parenchyma part of the model. we start to look after, maybe it's better if you see it in the television, we start to look after some interactions between cells. In red, you can see endothelial cells. In green, you can see astrocytes, and in blue, you can see pericytes. We start to look after some places in which these colors can be correlating in a merged photograph. So this interaction allows us to think that maybe this system can have phenotype and functionality in the model of blood-brain barrier. So remember that we said that cells were cultured, one side endothelial cells and in the other side astrocytes and pericytes and microglia. So after seeing that maybe in some areas the cells actually are interacting, we look for some specific points in which maybe this interaction can be closer. And what we found was that when in this video, you can see in red endothelial cells and in green astrocytes. Remember, one side of the membrane and the other side of the membrane seeded. In red, now you can see the reconstruction, like in every single slide of endothelial cells, but astrocytes remains 3D reconstructed. So, as you can see, in every single area in which the red mark is present, the astrocytes in green are interacting with this red mark. The other video is showing the same point, but with a different perspective. In which you can see now that the red and the green zones are interacting or are in the same plane on the top of the Col1 membrane and in the lower channel as well. So this analysis allows us to think that the cells are having contact between them across the Col1 membrane. And what is more important, the Col1 membrane has been remolded and allow the cells to put extracellular matrix de novo in this system. So, to test what will be the consequences of these interactions, both interactions of the cells, we look after the expression of tight junctions proteins as well as for de novo extracellular matrix proteins deposition. We compare the co-culture in the blood-brain barrier on a chip with the endothelial cells alone. And what we found, maybe the project does not allow us to see so well, but what we found is that with the blood-brain barrier on a chip co-culture, the expression of nitrogen, sonaloccludens 1 and claudin 5 is greater than when you only culture over the same system endothelial cells alone. So an important point here is the deposition of the novo extracellular matrix, because after that de novo deposition, we can think that cells are, as I said, remodeling the Col1 membrane, and what is more important, they are making like a new home for all of these kind of systems, so they can express the correct functionality. This video shows you how the nitrogen is deposited over the Col1 membrane. In red, you can see nitrogen. In white, nuclei. If you notice, this in the middle, you have like an empty space. This empty space will be the Col1 membrane. So in here, you can see this empty space. So in this empty space is the Col1 membrane, and this analysis shows us that nitrogen has been secreted in one side of the membrane and in the other side of it. That is very important because now we know that cells can this protein is mainly secreted by endothelial cells, but this also can be secreted by astrocytes and pericytes. But if we look for it we can see it in the both sides, now we know that cells are going to the other side or at least taking their projections to the other side and put this extracellular matrix in the other part of the cold-wall membrane. So this will be an indirect way to show that the cold-wall membrane has been remodeled. So these results allow us to know or to think that maybe in this model, this static blood-brain barrier model, we can have some functionality. And remember that the main functionality of the blood-brain barrier is to modulate the flow of molecules and cells from one side to the other side, to the peripheral circulation, to the central nervous system. So we designed an experiment in which we introduce to the upper channel, we introduce some dextran associated with fluorescein. And then we test and we measure how many of this dextran flows from the upper channel to the lower channel. We made that using a confocal 3D reconstruction, and we measure it a full hour. We test 10 kilodaltons molecule. We can say that a small molecule, and then a 4 kilodaltons molecule, that will be larger than 10 kilodaltons. And we stimulate the system with LPS for an hour, and with LPS and dexamethasone as anti-inflammatory molecule for another 24 hours, and then we test this dextran flow. So to measure this dextran flowing, we should at the very beginning know where the cells are. So we label them with a cell tracer, and after that we put the dextran fluorescein associated in the upper channel. So this kind of images will be the one that we analyze. So we analyze how much of this green dextran flow through this red part and pass to this part will be the lower channel. So what we have found? We have found that in the case, maybe I hope you can see it well. When you put the chips with no cells, that will be this line, all the molecules, the 10 and the 4 kilodaltons, have a very basal flow through the cold-wall membrane. When you put the blood-brain barrier on a chip, that will be this basal line, this permeability of the two molecules is quite reduced. This one will be for 4 kilodaltons, and this one will be for 10 kilodaltons. When you add LPS as a pro-inflammatory molecule, then you can see that the permeability of the both molecules rises. Of course, do not rises as much as the chip alone. And finally, when you put the dexamethasone as an anti-inflammatory treatment, you can see that in 10 kilodaltons, the values are restored to the control ones, but when you measure the 4 kilodaltons flow until 36 minutes of analysis, the values were lower than the control system until a kind of an hour in which the values get as the same as the control blood-brain barrier on a chip. So what this thing is telling us is that the system responds to a pro-inflammatory stimuli. And what is more, it is telling us that the system responds as well to an anti-inflammatory stimulus. So we can now start to think that this system can be used to test a wide variety of molecules to study neuroinflammation and to treat the neuroinflammation. These images in the bottom of the figure are bottom to top images. This one will be like a transversal image of the chip, like in the very beginning, like this one. That will be like a transversal cut, but in these images, you can see that when you measure the whole chip, the flow is quite conservated. What I'm trying to say is that the behavior of the flow is the same in all over the cold one membrane with the cells. So this is important because now we can say that the whole system, the whole part with cells co-culture on it, allows you to put to make this kind of measurements of permeability. So we test what happened with Claudin 5. Claudin 5 expression is one of the components of the tight junctions. And remember, the tight junctions were these ones that allows the endothelial cells to be very close between them. So as expected, we saw that after LPS treatment, the coverage all over the chip and the mean fluorescence intensity of the expression of Claudin 5 diminish. But with dexamethasone treatment, it rises, even though more than the control group. So this can explain us why we are seeing this behavior of permeability in the experiments. Finally, we test several cytokines to analyze how is the inflammatory environment inside this chip. So we take the culture media and analyze for these cytokines. What I want to highlight in these results is that, as expected, in LPS treatment, that will be the middle bar, all the cytokines get higher. But within these cytokines, IL-6, IL-22, and IL-10, which values are not shown because we almost have measured this cytokine, all of these three cytokines get higher after a pro-inflammatory stimuli. That is important because maybe, before that, IL-6, IL-22, and IL-10 has an anti-inflammatory capabilities. So maybe what we are looking is, at the same time, a response to a pro-inflammatory stimuli, but at the same time, the system that is a multicellular one is trying to recover the homeostasis, secreting anti-inflammatory molecules as well. So this is an hypothesis that should be proved in further experiments, but it's very important because in the nature, the central nervous system and almost every structure or organ in which the inflammation is performed aims to restore its homeostasis. So these results shows that maybe this homeostasis is trying to be reached in the system. Okay, as a conclusion, and now we can say that blood-brain barrier on a chip is sensible model to pro and anti-inflammatory stimuli. So this is important if we want to have a great larger scale molecule test. Then the blood-brain barrier on a chip model allows the evaluation of the effect of different stimuli over the different components of the model. Remember that we can see what happened with cells in a very specific way, or even though with what happened with extracellular matrix components. Dexamethasone recovers the functionality and barrier structure of the blood-brain barrier on a chip model. And cold-wall membrane is a good cellular scaffold that will be useful to blood-brain barrier functionality and the cellular interactions in this kind of models. And talking about some perspectives, we need to incorporate medium flow to reinforce the biomedical statement in this kind of model. We need to make greater characterizations, maybe tree measurements, special light transporters and receptor expressions, and cold-wall membrane remodeling and extracellular matrix de novo deposition, because I only study one of the multiple extracellular matrix components of the basal membrane. Then incorporate biosensors to the model that will be useful to study in vivo what happened with the concentration of cytokines, because what we have saw in the results, it's 1 point only in a timeline. So we can analyze in vivo what is happening with these ones and maybe prove this hypothesis of getting back of the homeostasis. And then put a multi-blood-brain barrier in a chip in a single plate. Imagine you have 96 well plate, but instead of the wells, you can have 10, 12, 18 chips in the same well. So then you can have a multi-molecule test in a single well, and then you can have a great scale analysis. And finally, I want to make a conclusion highlighting the use of these two biomimetic models, organoids and organs on a chip. Organoids allow us to resemble the development of the illnesses and the three-dimensional structure of the organs. But organs on a chip allow us to introduce some physiologically relevant variables like blood flow, shear stress, in the heart, or along the contraction of the environment. So an interesting thing would be to join together, and actually some of the groups that are collaborating with the LAMS Biodit now are joining long organoids with organs on a chip. But an interesting thing will be joined different organoids of different structures inside microfluidic devices. So you can have the advantages of both kind of modeling in one single strategy. And imagine that talking about specifically from the neuroscience perspective, if you can have an organoid that allows you to study aging, but in the very first part of the aging, when you're inducing the model, and then you can analyze what happened with the organoids all over the time inside the microfluidic device. And from here, the options are almost endless. And how these kind of models can look like. You can have this organoid in the lower channel, then in the upper channel you can have maybe some endothelial cells. You can have a peristaltic pump in a closed flow of medium that will be stimulating this organoid and recovering whatever this organoid is producing, and then put it back in a reservoir to analyze it. And then you can also have this upper channel in which you can put inside some drugs, some molecules, whatever you want, and see maybe in these drugs goes through the endothelium and reach the organoid and make some effects on the organoid. All of this can be seen in live with a microscope because, as I said, the organs on a chip allow us to see them in live. Yes, in live. So in the very top, in the very bottom, we can have some biosensors to measure maybe tear in the endothelium and measure how this system is responding to some molecules. And finally, I want to thanks all of our collaborators, my PI that will be Eda Shuto, and my second PI that will be Gladys Fragoso in the same lab, and many people working in this project because as you can notice all over this event, you need a multidisciplinary team to join and to develop this kind of experiments and research. Thanks so much. $50 Sí. Good, good.
Nicolas, how long does it take to change the collagen 1 membrane for nidogen membrane in your chip?
Okay.
How many days or weeks or I don't know?
I have analyzed the photos and the video that you have seen is an analysis for 2 weeks of co-culture. But for sure, we need to make a time dynamics of how in every single point the cold one membrane is removed by the cells. But what you have seen is
After 2 weeks.
2 weeks co-culture, then you can see this kind of results. And actually, there's some literature that say us that in a shorter time, the extracellular matrix proteins can be secreted as well. But well, we need to study that in more depth.
And when you have your membrane enriched with nidogen, then you put LPS to your chip?
Yeah.
Okay.
This very first part of characterization is by the 2 weeks, and after these 2 weeks, we know that the system is like stable. Then we make the experiments of all the results that you have seen.
Okay, thank you. And the second question is, these changes in Claudin 5 is related to changes in gene expression, or the protein is degraded by endocytosis, or have you ever explored the mechanism about the downregulation of Claudin 5?
Mm-hmm. This is a very interesting question because it depends in quite factors. One of these factors could be the extracellular membrane, the basal membrane, that it is known that in other endothelium cells, as well in blood-brain barrier, that when this basal membrane is degraded, the expression of tight junctions diminish. So that will be because of the physical disattachment of the extracellular matrix. But this will be because of a downregulation of gene expression as well. And actually, in other endotheliums, like in liver, inducing the inflammatory process with LPS can trigger these kind of changes as well. So we haven't explored it in depth because we will take a very long time to standardize and this project. But for sure, we need to make some, as I said, some deeper and more robust characterization to see what is happening in every single part of the model.
Okay, nice talk.
Thank you.
Thank you. I'm just curious as to why you didn't include the flow in the first place. I mean, it seems that from your lab, it wouldn't be really like a technical challenge or anything to include some flow. So I'm curious as to why did you decide to start first with the no flow and then go to the second stage, let's say, with flow, as you're putting in your perspective.
Yeah.
And in the same sense, how critical do you think it's going to be in terms of how different are the results going to be once you have this shear stress over your cells?
Mm-hmm. Yes, shear stress is very important. One of the at the very beginning, we start with this experiments with no flow because we wanted to answer this question, that if this native extracellular matrix will allow us to have a model
without flow. The second reason is because technically, remember the height of 200 micrometers of the channel in which the cells are seated. Our peristaltic bumps have like a low range, more or less 5 microliters per minute. But when you pass this medium through the culture area, this very small transversal section of the chip increases the velocity and in advance the shear stress. So what we have noticed is that with this infrastructure that we have, the cells are disattached. But as we continue with the experimentation, we notice that even though this is an static model, it serves as a blood-brain barrier on a chip model to test permeability and to test different molecules. And when we introduce the flow, what I am expecting is the more more robust or more tight junctions. So this is the main consequence of the shear stress. Another thing that will be happening is that the cells can polarize to the direction of the flow of the sculpture medium. So we are expecting a lot of things, and finally, that will allow us to introduce like chronic stimuli and chronic as well treatments, so we can see what happened all over time.
Thank you. Very nice work.
Yeah.
Thank you, Nicolas, for the nice results. So you showed, I think, convincingly about how your model can reproduce pro and anti-inflammatory effect. But what about the basal functioning? How can you compare it with the real system in terms of permeability? And I mean, can you test different molecule, or do you expect further progress to be made, or in efficient, like for the efficiency of the barrier as compared to the physiological one?
Yeah, that's a very interesting question actually, because and a thing that we haven't made is to compare these things with in the same conditions with an animal, because we are using murine cells. But if we look after the papers, we can see a similar behavior of the flow of dextrans after the development of the trigger of nerve inflammation. So for sure, the values, the concentrations, and won't be the same because you are not using the same system, but the behavior will actually is similar to what we are looking in vivo models. Unfortunately, we haven't tried to compare in our experiments in the real time mice, but for sure we need to do that. And when we are talking about another molecules, will be the same. Trying to compare it with literature and then see what happens in our model. Yeah. Thank you.
¿Alguien tiene alguna otra pregunta? Bueno, muchas gracias, Nicolás, por habernos acompañado el día de hoy. Muchas gracias a los asistentes. Vamos a continuar con nuestra segunda ponencia de la tarde con el doctor José Luis Menchaca, quien nos acompaña vía Zoom. El doctor José Luis Menchaca es un destacado investigador de la Universidad Autónoma de Nuevo León y su trabajo se centra principalmente en el estudio de la biofísica, la fisicoquímica de superficies, interfaces, y su investigación está centrada principalmente en el uso de microscopía de fuerza atómica.
So people, can you hear me? Probably I am mute. Hello, hello. Good afternoon. Can you hear me?
Hola, denos un momento, por favor. Están conectándolo a las bocinas del auditorio,
Ok,
pero sí ya lo podemos escuchar. Un momento.
gracias. ¿Usted me avisa, por favor?
Sí.
Yo sí.
Thank you so much. Thank you so much. No, I haven't said that because over time, but it is made. You dissolve cold one in acetic acid, and then you put it in like a frame, a rectangular frame. Then the solvent could be evaporated, and after that, the cold membrane is done. The guys from the lab, the national lab, needed to standardize the concentration and the amount of solvent and the evaporation conditions to make the membrane permeable, um, ¿cómo se dice? That be elastic one, so and resistant because sometimes it can be broken when you take out and try to put in the chip, then you break it. Three 360 nanometers average. Yeah. Like by the frame, then you in your lab can put the cold one, then the acetic acid, put in there, and that's all. Yeah, yeah. Yeah, 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 yeah.
Muy pronto y que no demore más eso. De nuevo, muchas gracias.
Yes, because to make like a proposal in concordance of my PhD results. That's what you are saying. Nowadays, we are starting.
No sé si nos puede
like a new
escuchar.
project
Sí, los
in which
escucho.
another student,
¿Ustedes me escuchan?
will try
Y si
to
no,
standardize
¿podría
a
escribírmelo en el
3D,
chat?
Sí, los escucho.
model. We were thinking
Voy.
that in particular, the brain vessels will be kind of easier in between a lot of brackets easier, because we can put inside the model the astrocytes and pericytes
Pero sí es
that
acá,
will
¿no?
be like feeders
No se
cells
conectan.
and
sin
homeostatic
HDMI, el audio.
maintaining cells. So
No, porque ya
the endothelial cells from brain
Ah, ok,
vascularity
entonces pongo
is getting like a
en Connect y entonces
three-dimensional
dice que si no se escucha.
tube
Mi-
architecture. Well, we're starting that. So
Pero
maybe
parece que ustedes no me escuchan, ¿o sí me escuchan?
propose the project. We can. Oh, I hope we can have another results, so we can make more.
A ver, ¿puede hablar de nuevo?
Proposal. I hope he's
¿Me escuchan
starting
o ya?
actually this week.
¿No me escuchan?
Ah, ok. A ver, ¿puede hablar de nuevo, por favor?
Sí. Que si me escuchan, ¿me escuchan? ¿Sí?
Sí, le estamos escuchando, pero queremos ponerle un poco más de volumen.
Ok. No sé si estoy muy lejos de mi computadora, tal vez. Ahora déjenme hacer algo.
Ok, sí, ya lo tenemos aquí.
¿Sí?
Sí,
Perfecto.
mire. Así que una disculpa por la demora
No.
y por todos los problemas, verdaderamente.
Ya se ve mi pantalla, pues.
Sí.
Es mi presentación.
Ajá, ya está la presentación, ¿sí se ve?
Ok, perfecto.
Igual si puede prender su cámara, estaría perfecto, si no, no se preocupe.
Sí lo puedo prender, pero ahí estoy.
Mire, muchísimas gracias.
Ok, entonces ya estamos listos para empezar.
Sí.
Okay. Well, we are ready to start. The subject that I want to talk today is about mechanotransduction by atomic force microscopy. First of all, I want to thank Tatiana Flordelizo for the invitation to this to show our work, and thank you to the people that is in the room. Well, first thing I want to say is it is my outline. I first want to talk about the introduction, about what is atomic force microscopy, the field work about methodologies and methods, and a second work about HT29 cell interaction with doxorubicin, and a third work about viscoelastic properties of MG63 cells during the mineralization process, and a final work about relationship between morphology and viscoelastic properties. I think most of the people knows the field. I am physics, and I think I am the person that less know this field. And this is basically for me what is a cell. The cell is a basic structural and functional unit of living organisms. We have two kinds of cells, animal and plant cells. But the important thing here is what is the definition of mechanotransduction? Is the processes by which cells sense and respond to mechanical stimuli. And this mechanical stimuli depends on many factors. For example, shear stress, gravity, the ESM remodeling, strain, intercellular signaling, and these have importance for several biological processes, like tissue repair and this progression. In this field, I think we are in the part of the cancer cells where is studying now cancer cells. And in this sense, we can see the difference between cancer cell and normal cells in terms of the shape, nucleus, growth, maturation, communication, visibility, blood supply, oxygen, glucose, energy efficiency. Sorry. And nutrients preference, etc. Then the system we're trying to understand is really complex. And in the case of cancer, try to understand, for example, metastases, how these metastases have adaptation, have change in structure, change in morphology, change in mechanical properties. This is in the field we are working right now, and but we want to go further and try to understand what's happened with the biomarkers and what happened when the treatments in the cancer cells. Then another important thing here is what is the difference between cancer in terms of the cell morphology for health cells in the left and in the right, the cancer cells. In the case of the cancer, is big and irregular nuclei, loss of differentiation, exaggerate characteristics, variety of shapes and size through the same tissue, and uncontrolled and disordered cell division. Instead, the health cells, it has small and uniform nuclei, different cells according for the function, similar shapes and size through the same tissue, controlled organized cell division. Then, in this field, we have to think about what are the physical characteristics of the cells, and we can find that the cell have behavior as viscoelastic material, and here we have two different behavior. In the case, the water, like a water is a fluid, an Newtonian fluid, and in case the spring is a elastic solid, and we think that the cell has the behavior intermediate in between Newtonian and elastic solid. Then we can describe the Newtonian fluid like strain relationship by his derivative, and the elastic solid like the Hooke law, a relationship between stress and strain, and this factor is the Young modulus. There are several techniques to study viscoelastic properties of the cells. One of them are shown here. One is atomic force microscopy, microfluidic methods, micropipette aspiration, parallel plate technique, magnetic twist, cytometry, magnetic tweezer, optical stretcher, optical tweezer, acoustic methods, and particle tracking microbiology. In our case, we are using atomic form microscopy. It means that we are studying cells that are attached to the substrate, and well, this is the. I'm sorry for the Spanish here, but here we will see later. I think the first works about mechanical properties of cancer cell was by Malgozar Taleca. They distinguish between cancerous cells and normal cells. It means health cells, using a tip that making an indentation in the cells, and they measure the elastic properties of the cells using the relationship like a spring. Then they show that for the case of cancer cells, the elastic modulus is lower than the normal cells, and this has the property that the indentation is bigger in the case of cancer cells. I think it was the first works about differentiation between cancer and healthy cells by atomic form microscopy. Then we have the crazy idea that establish a universal classification for cancer cells based in morphology and mechanical properties. Our questions are which methodology is better to measure the mechanical viscoelastic property of the cancer cells? Which mechanical model represents cell behavior more accurately? Which parameter gives us more accurate quantitative information on cell morphology? Will indentation speed alter our results, and how? Well, until now we have more questions, but they are the first question that we have. Until now, we have working with these three cell lines: MDI, MEV, breast cancer, DE 145 prostate cancer, MG 63 osteosarcoma cells. Then, what is atomic form microscopy? Atomic form microscopy is a technique that helps us to study the morphology of the cells in this case, but it can go beyond. In this case, to make an indentation over the sample and to measure elastic properties of the cells. For the EFM, we have different strategies. First of all, an EFM use a very fine tip, known how cantilever, which moves over the surface. But in this work, most of the time we use for detection. It means we can make indentation with the tip onto the cells and to see what is happening with the mechanical properties of the cells. Okay, what is the advantage of the atomic form microscopy? First of all, we can work in buffer and ambient conditions. The people is working about dynamical mechanical properties using different strategies like single frequency, position dependent, frequency sweep, or time dependent. The other advantage is the temperature, pH, and humidity. We can control these factors. and the people is going forward implementing simultaneously another optics techniques like DIC, epifluorescence, fluorescent, and super resolution, and also some people is doing FRET, for example, and the people also is using electrode and patch clamp for to try to at the same time make the different measurements and obtain different properties of the cells. What is there is an issue in the atomic form microscopy. I will explain later about this part. But we know that the cancer cell in this case is viscoelastic, basically because we can measure. Here I have the force distance curve. One is for the when the tip is loading, and the other is when the tip is retracting from the cells. And we can see this difference, and this difference between the approximation curve and the retraction curve is due we have some energy dissipation in the medium. The people has working with pyramidal tips, conical tips, cylindrical tips, spherical tips, and wedge tips. The people is working a lot with this technique to measure mechanical properties of the cells. The first thing that they want to describe is well, what methodology is better for our study. Well, here we have basically two methodologies. One is the relaxation curve. That it means I have force versus time curve, and here the red part is when I am approaching to the cell. I am indenting to the cells, and then I stop the force and I start to see the relaxation of the cell, and in a while I will retire the tip of the cells. The other methodology is about force distance curves. That means I will approach the tip to the cell. Here I will touch the cell. In this tip, in this point, I will touch the cell, and then I will make indentation, and I will make a retraction, and here I will the tip will be free. But for to do this way, I have to change from the a curve that is force versus distance to a curve that is force versus time. And in order to do that, we need to calculate these two equations that normally takes takes time, and also takes it looks like it's really complicated. Then we do the two experiments to make a comparison. Let me explain better here. First, we use force distance curves, and we believe that the force time curve is a better methodology for obtain the viscoelastic properties of the cells. Here you will see
a force distance curve is acquired by bringing the cantilever tip into contact with the sample surface.
Spherical tip
The
is
shape of
approaching
specific
to
regions
the
of force distance curves offer
to
insight
the cells
into
and
different mechanical
make an
properties,
indentation in the
such
cell.
as adhesion,
Here you
young
can see how the
modulus, etc.
we have some penetration, and the after a while I have to, when the curve comes to be constant, I retire the tip, and now I have to make a fit in this curve basically. This is the experiment that we have to do in our experiments. Okay, then as I said before, the cellular viscoelastic, the evidence that the cellular viscoelastic is because we have some dissipation, energy dissipation in this kind of curves, force distance curves. Then we need to go another subject about the mechanical and viscoelastic models. We have in the literature several viscoelastic models. In this case, the Snedden or the Snedden modification is just for the elastic part, but we have fractional Kelvin, fractional Zener, and also we have Maxwell generalized model that every equation is related to every model is described here. And you can see here the realization is related about first is the Young modulus, and this is the time relaxation. In the case of the Maxwell generalized, I have at least two exponential. It means I have 1, 2, 3, 4, 5 parameters to try to fit the relaxation curve. And in the case of the fractional Kelvin, I have 1, 2, at least 3 parameters to try to fit this model to our experiment. And also I have a fractional Zener model that has 1, 2, 3, and 4 parameters to try to fit the experiment. Then the first question is, which of this model can fit better to the experimental results? Here you have the 4 models that we studied in this work, and here is the graphical representation of each one. Well, try to describe if each model is not representative for this talk, but if you want to know more about the generalized Maxwell or about the model that we use, we can discuss later in this talk. Our point of view, we think that the fractional Zener is the best model to try to interpret the experiments, and I will show you why probably in the next slide. Well, at the first time, the SLS model, it doesn't fit for the experiments. In the case of the generalized Maxwell model, we have many parameters, and we say, okay, if we have many parameters, we think that it fit perfectly, but to understand or to try to represent the behavior of the cell is difficult to describe in terms of 6, 7, or more parameters, and we are trying to understand the cell with the less parameter to try to understand the behavior. Then it was reported in this article 1 year ago. But the thing that I want to point out is look at the indentation to measure this indentation for each cell line. You have here in the graph the force versus penetration, in this case indentation. If you take, for example, 20 nanonewtons, you will see that the penetration or the indentation of the tip at the cell, it will be different, and is independent of the force. And you will see here in this system as well the same behavior, and also in MG63 you will see the same behavior. And then the people doesn't discuss this behavior a lot in the so much in the literature, but we're trying to understand this behavior. This is the results for the different models and different parameters of the models. The E0 is the okay. In this graph, I am showing you the blue. The blue background is for one methodology, and the red background is for force retraction curve or force relaxation curve, and the blue background is for force distance curves. And you will see every result for every parameter, and here you have the model. This is for the elastic part of the cells. Then the most important here is to see what is the behavior of the time of relaxation in the case of the fractional Zener and fractional Kelvin models, and also this parameter alpha, that is related with the fluidity of the cell. Then when these results, we can conclude that the best model to represent the cell is the fractional Zener model, and the best methodology is the fractional, the force relaxation curve methodology. Here you will see the results in terms of the fit. How good is the fit is represented in this graph, and also in this other graph you can see the IC value for all the models, where we can see in this case the fractional Zener model is is better than the other. Particularly, we are working with fractional Kelvin because the special case of this model is a power law. This represents a power law in the cell. What? Okay. After this first work, the next work was to what is the interaction? What happened with interaction between HT29 and doxorubicin? In this case, we use different tips. A tip that is a natural tip that comes from the company that with a tip, and a modified tip that is a spherical tip that is the size of the 30 microns. It means it's close to the same size of the cell. As you can see here, this is 20 microns. That means that in this case, we are making an indentation with a tip that is around 10 nanometers. And in this case, we're using a spherical tip that is around of the size of the cell. Then the result here gave us almost the same thing. It means all this is the relative change because all these measurements are normalized when the control, when the value of the control on the control cells. In this case, we make a control. It means the cell without any treatment. And we measure different time of the treatment, 24 hours and 84 hours after the treatment. And in this case, this graph shows us the different behavior when the fractional center model that this said that in terms of the time of relaxation, we can see difference, and in terms of the alpha parameters, we have also really difference between the two systems, and between 24 hours and 48 hours in the different treatments. Here you can see the behavior of the young modulus. The young modulus for the control for the treatment 24 hours. But as we said before, the cell is viscoelastic. It's not just elastic, because you can see here in the case of the tip that is just 10 nanometers, you cannot see the difference. You cannot see the effect of the drug really in the young modulus, only when the young modulus. Then here is the fit for each model. In this case, we can see the difference. This is the residual sum of the difference for each cell, and you can see here that the fractional center that is in green is the best the best fit for this case. We continue with another work that is about viscoelastic properties of MG63 cells during the mineralization process. In this case, we have MG63 cells that are in the osteogenic medium for 3 days, 7 days, and 40 days. We have 3 different mediums: osteogenic medium, hydroxapatite, and hydroxapatite plus nanoparticle silver in the medium. And we want to see what is the effect of the nanoparticles in the medium and what happened when the viscoelastic properties, and if the model can distinguish between every different system, and also if we can describe the evolution in the time. Here you can see the graph of the elastic properties of Young modulus in depending of the medium, osteogenic medium, hydroxapatite, and silver nanoparticles. And different color means 3 day, 7 day, and 40 days. And also you can see the parameter alpha that is related with the fluidity of the system. And we can observe that, first of all, that the parameter is really sensitive to the system. We can see the difference. At the beginning, we can observe that the 3 days is there is no difference between the systems, but the difference comes in 3 days and 7 days for each system, and it can describe by this parameter, and also for the relaxation time. We can see the difference, but in the case of the Young modulus, it's not clear what is happening, because normally when you measure the Young modulus, as explained before, you have big scatter graphs in each system. The question is still is open about what means that we have this big scattering in the medium, in the graph. Here you can see a picture about the system. To describe the system, 3 days. This ABC is for different system, and this row is for the 3 days, this row is for 7 days, and this row is for 40 days. And here you can see the calcium production in the system due to a protein that is in the system. Yeah, then you can see different images of atomic form microscopy of the system, and you can observe that the system is 14 days is growing, and it means that the elastic properties and also the morphological properties of the system are different in each step. In this case, we measure with different force the system, and trying to say, well, probably we are using a lot of force to make the indentation in the cell. And we go to another experiment. We say, okay, bigger than 80 nanonewtons are this graph. The red part and the blue part is less than 18 nanonewtons, and also we saw the same behavior in the tree system as similar with the tree system that we have studied before in the case of 3 different cell lines. We think that this behavior is due the morphological change in the system, but it's an hypothesis that we have, and we want to corroborate with different systems. The first conclusion, this part is, wow, the Young modulus is not sufficient to study mechanical behavior of the cells, and viscoelastic properties of the cells obtained, but relaxation curves and the fractional center model describe the different scenarios studied in more detail. The viscoelastic properties can help elucidate the mechanism of action of new treatments, as doxorubicin was studied in this work. Then our hypothesis is, well, if we are able to measure correctly the morphology of the cell, probably we can make a relationship between morphology and viscoelastic properties. Then, in order to do that, we look for the literature and say, what is the parameters that describe the morphology of the cells? We find that, for example, perimeters, cell area, aspect radio, convex hull perimeter, convex hull area, circularity of form factor, ellipticity. However, these parameters doesn't describe really the shape of the cell. We think that these parameters are qualitatives, and we need to go further and make a quantitative description of the morphological properties of the cell. Then we propose to use LOCO-EFA. LOCO-EFA is a lobule contribution elliptic Fourier analysis to build the morphology of the cell. In this case, is in 2 dimensions. And one thing important here is the description of this ELN that is built by the first harmonic in the first elliptic harmonic. It means it's the sum of lambda 1 and lambda 2. And with this ELN, we can describe the morphology of the cell. As we can see in these figures, the complexity of the form that I want to describe is dependent of the harmonic, or the number of the harmonics. For example, here we have 7 harmonics, and we have 16 because it's more it's a shape more complicated. Then another representation that we have, another description that we have in the literature is these another parameters, but still they are qualitatives and doesn't give me the real shape of the cell. In order to do that, and as we don't have an microscope, atomic form microscope coupled with optical microscope, we decide to build optical microscope by Raspberry Pi and an objective, and try to describe at the same time with this experimental arrangement the mechanical properties, the viscoelastic properties, and the morphological properties. You can see here the camera, the top view camera is like this, and the bottom view camera is like this, and this, when this bottom view camera helped me to see the morphology of the cell. Then after we adapt this microscope using 3D impression and an optical microscope, an optical objective, sorry, we are able now to describe the morphology and the relaxation curves of the system. And here we have an example. And the important thing here is we propose a parameter what we call shape complexity, and we decide to make different strategies to see that the less than 60 harmonics, we have most rounded cells. Between 60 and 19 harmonics, we have in the middle, and bigger than 90, we have triangle and shaped and polygon shaped cells. In this case, we think we have more quantitative description of the morphology of the cells, and also by local EFA, we can make we can see the behavior of the area, the perimeter, the circularity, the aspect ratio. If you look at the aspect ratio, you will see, for example, that this is for the circular shape, and this is for the triangular shape, and you can see that the aspect ratio is basically the same relationship. It means that you can make a confusion between rounded cells and triangular cells by using this parameter. In this case, we have shape complexity defined like every ln, the sum from 3 to 50, and it is, the graph is here. We have two experiments, and we can observe that practically the behavior is really similar, and you can make a classification of the cells in this this methodology. And what is the behavior of the viscoelastic parameters? We can observe that the viscoelastic parameters are similar for the two experiments. This is the second experiment where we can see the cells are grouped by basically by the number of harmonics in the system. Well, the other thing that we want to know is what happens if we make an indentation with different velocity. If we make an indentation with different velocity, we will see different changes in the alpha parameter and also the E0 parameter and the relaxation time parameter. In this case, using just the fractional center model. Well, in this part, we have the conclusion that the shape complexity metric provides a high quantitative classification that is capable to distinguish cell by number of prominence in the lobes. And Kelvin and Zener model describe cell behavior. However, the Zener model provides more information on fluidity. More simultaneous studies are needed. We have, until now, just one system, in this case, MG63 cell line. And the other important thing is what is happening when the component is in the cytoskeleton. I think if we can cope fluorescence, we can describe these components of the cytoskeleton, but we need more experiments as well. Okay, this is the team. We are working, Doctora Marisela Rodríguez Nieto, Doctora Diana Zárate, that is in the biological part, Alejandro Flores Mayorga is a bachelor student, Axel Fernando is a bachelor student, Jesus Valentín Galindo, Joali, and Caleb as also bachelor students. Right now, Berta Guadalupe is a master student working in this experiment. And well, the acknowledgement, Consejo Nacional de Ciencia y Tecnología y Humanidades, by the project CONACYT, Facultad de Ciencias Físico-Matemáticas, and Laboratorio de Inmunología y Virología. Here's some reference, and I think it's all for me right now. If you have questions or you have doubts, please let me know.
Muchas gracias, doctor Jorge Luis. ¿Alguno de los presentes tiene alguna pregunta?
Hola, doctor.
Hola.
Hola.
Gracias.
¿Prefiere la pregunta en español o en inglés?
Como usted prefiera.
Okay, in English then. So for everyone. So when people talk about like this, I don't want to call it biosensors, but like these strategies essentially for diagnosis, oftentimes techniques like AFM is, I guess, criticized because it is not as easy to implement, like in a portable, user-friendly manner compared to optical, electrochemical, or other kinds of methodologies, right? So in this sense, could you give us some perspective of, do you think at some point AFM or techniques alike can make it to like the widespread public, or is it going to be always like specialized users that need to operate the instruments in order to?
Yeah, that is true. It's a really interesting question. I think we are going in this way. We need to have a better technique. What is the problem? What is the objective at the end of these studies, of this research? That we want is to go to the hospital and to study the system in the real time and with the real people. But imagine an atomic form microscopy has the cost around $300,000, and the optical microscope is also really expensive. And for a hospital that has this money, probably have the money. Some people in USA, some people in Europe have this system in the hospital, but it's not easy. And if you think in terms of the atomic force microscopy, the only that we need is to approach the tip to the cell and then retract the tip. It's the only thing that we need in this case. And we want to simplify this approach in order to make an instrument more efficient, more low cost, I think. We're working in that, really, we're working in that. Because, yeah. Thank you for the question.
¿Alguien más?
Hola. A short question on the decomposition of shapes that you use for analyzing the cell shape with some harmonics. I'm kind of surprised that you have 60, 90 harmonics. Plenty of other image analysis systems use maximum 15, 20, such as Zernick polymers, what is it called? Yeah. So basically, you have other type of potential polynomial decomposition, such as Zernick and so, and they usually use 20 max parameters. Can you comment on this super high number of harmonics? Because obviously you start from symmetrical shape and then you go for very asymmetrical ones. So if with 90 it's okay, potentially with 122.
Okay. Let me make a comment about that. You mean where is it? Probably here. Yeah, you're right. We are working until 50, if you can see here, because after 15 harmonics, it starts to oscillate, and this is why we in this case we use just 50 in the case of the complexity. But in order to obtain the real shape of this figure, for example, for example, this triangular is the cell number 23. Really, you need more than 90 harmonics to describe relatively well the shape, because before is not completed. When you make the the reconstruction of the cell is not well completed, and there is a parameter that we have to follow. That is the difference between the theoretical reconstruction and the experimental. And yeah, it's difficult. It's difficult for us to. But well, this is our first approach to try to solve this problem. I don't know if it was clear to respond to your answer, your question.
Yes, thank you. ¿Alguien más tiene alguna pregunta?
Hi, I'm not familiar with this type of analysis, but I was wondering if this is like an open source tool or I mean the LOCOEFA analysis.
Yeah, we're trying to do that. The open source, sorry, the LOCOEFA is a paper around, I don't know, probably 10 years ago, almost 10 years ago. And it's not open. I think it's open source, but it's in C++. Yeah, it was described in C, but building in C++. And we are now making this analysis in Python. Probably in some time it will be open source.
It would be nice. Thank you.
Yeah.
¿Alguien más tiene alguna pregunta? Ok, creo que muchas gracias, doctor Jorge Luis. Muchas gracias a los asistentes y con esto damos por terminada nuestra sesión del día de hoy. Muchas gracias.
Gracias.